You didn't open this video by accident. You came here for peace, but what you'll find tonight goes far beyond sleep. As you close your eyes, you'll hear the quiet side of the cosmos, the stories hidden behind silence, the secrets drifting through the dark between stars. Keep listening, because what 3IATLAS revealed will change the way you dream of space forever.
Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video.
When something from beyond our solar system enters our sky, the ordinary rhythm of astronomy stops. Every telescope swivels, every data stream opens, and somewhere in that flood of numbers, a quiet realization unfolds. The visitor is not one of ours. That's exactly what happened in July 2025, when a faint streak appeared on the nightly scans from the Asteroid Terrestrial Impact Last Alert System, the network the world calls simply ATLAS. Within hours, observatories from Chile to Hawaii were buzzing. The trajectory was wrong, the velocity too high, the orbit unmistakably hyperbolic. Another interstellar object had arrived, the third ever confirmed, and in a gesture of poetic symmetry, it inherited the name of the very system that spotted it, 3IATLAS. At first it seemed routine, a continuation of the lineage begun by Oumuamua in 2017 and 2I Borisov 2 years later. But routine lasted only a week. When astronomers tried to unwind its path, to trace it backward through the Milky Way, as they had done for comets and asteroids countless times before, the math collapsed into silence. Every model, every simulation that should have pointed toward a parent star dissolved into emptiness. 10 million years of reverse motion through the galactic map revealed nothing. No encounter, no gravitational nudge, no plausible birthplace. It was as if the universe had deleted the return address. To grasp the magnitude of that failure, you have to imagine the process. Normally, when a wanderer like this appears, scientists treat it like a cosmic detective story. They plug its orbital parameters into databases built from the European Space Agency Gaia mission. Hundreds of millions of stars with precise positions and motions, and then run the film backward. The technique is nicknamed the dashcam rewind. In principle, if you wind far enough, every curve of the object S-path should lead to the intersection where it was flung free of its home system. That intersection is the smoking gun, a stellar encounter, a planetary slingshot, the moment of ejection. But 3IATLAS refuses to play by those rules. The first team to announce the anomaly described it politely. No statistically significant origin within the local sample volume. In simpler language, they looked everywhere within roughly 1,600 light-years and found nothing capable of giving it the push it carries. Even the closest candidate star, catalogue number 36863591389529611264, passed too far and too fast to matter. The computed velocity change was less than a millimeter per second, a whisper in the vacuum. For something traveling nearly 60 kilometers each second, that is effectively zero. The paradox hardened quickly. Here was an object moving like it came from the galactic thin disk, meaning it shares the general motion of young ordinary stars, yet it had no discernible parent among them. It was a local in motion, a stranger in origin, an orphan that behaves like a native. That contradiction spread through research institutes like an electric rumor. Within days, Hubble trained its optics. The James Webb Space Telescope rescheduled precious infrared time, and dozens of ground observatories joined in. If we couldn't find where it was born, maybe we could at least learn what it was made of. Before those spectra arrived, the data scientists kept staring at the orbit itself, trying to make sense of its impossible pedigree. Some blamed measurement error. Maybe the initial astrometry was off by a fraction of an arc-second. Others suspected hidden perturbations from unseen bodies or systematic biases in the Gaia catalogue. But cross-checks from independent teams produced the same emptiness. The more precisely they measured, the more complete the void became. It was as if the cosmos had conspired to erase the breadcrumb trail, one gravitational footprint at a time. In the language of orbital mechanics, 3IATLAS travels on a trajectory with eccentricity greater than 1, a mathematical signature of something unbound to the Sun. Once it swings past perihelion, the point of closest approach, it will never return. The solar system will keep most of its rocks, dust, and comets forever, but this traveler will slip back into interstellar darkness, carrying with it a story we still can't read. Astronomer Leila Perez, one of the early analysts, described the feeling of that realization in a conference interview. It's like tracing a family tree and discovering that your DNA doesn't exist in the record of human life. The metaphor stuck. Journalists began calling 3IATLAS the ghost object, something that exists, moves, and shines, but leaves no ancestry behind. That label proved prophetic. When the first spectroscopic glimpses from Webb came in a few weeks later, the chemical story was as uncanny as the orbital one. But we'll get to that. Right now, at the start of this 2-hour journey, it is worth lingering on what it means to encounter an object whose past cannot be reconstructed. The universe, as we understand it, keeps immaculate records. Every force, every orbit, every photon obeys equations that can, in theory, be reversed. If you know all the initial conditions, you can rewind time like a perfect film reel. Yet here was a case where our instruments, the best humanity has ever built, return nothing but static. Somewhere between mathematics and measurement, information had drowned in chaos, perhaps not lost in an absolute sense, but scattered beyond retrieval, like ink diffused through an ocean. Imagine standing on a windswept desert and finding a single glass bead half buried in the sand. You pick it up, turn it under the light. It's smooth, cold, flawless, and utterly foreign. You could trace the dunes for miles, sample every grain, measure every gust of wind, and still never find another bead like it. That's the predicament of astronomy when it confronts 3IATLAS. A perfect stranger dropped into our front yard, bearing witness to processes that happened before the sun had planets. This realization sends a quiet shiver through the field. For decades, scientists have dreamed of mapping the galaxy's chemical evolution by studying visitors like this. Each interstellar object, a messenger carrying the signature of its birth star, chemistry. Trace its orbit, measure its volatiles, and you can build a mosaic of planetary systems across the Milky Way. That dream collapses if the orbits themselves fade into noise. Without ancestry, chemistry loses its context. The bead remains beautiful, but mute. Of course, scientists are patient. They know the difference between untraceable and untraceable for now. Future data releases from Gaia, deeper radial velocity catalogues, and next-generation infrared arrays might one day tighten the error bars until a faint connection appears. But for now, the mystery stands. The third interstellar visitor known to humankind has no home address, no gravitational fingerprint, no past we can follow. And so part 1 of this story ends where the investigation began. In that moment of collective awe when an algorithm flagged a moving dot in a sea of static and someone realized it wasn't T from here. Before the debates about chemistry, before the polarization curves and spectral ratios, there was that first chill of recognition. Something ancient and unsourced had crossed the boundary of the solar system and was now, for a brief season, illuminated by the sun. Stay with me, because as we follow this ghost through its brief encounter with our star, we'll uncover puzzles that reach far beyond astronomy. Questions about how information survives in a chaotic universe, how matter remembers its birthplace, and what it means when even the cosmos forgets its own children. For weeks after its discovery, telescopes across the world and in orbit stared at 3IATLAS as if afraid to blink. It moved slowly against the background stars, a dim ember trailing a faint haze, ordinary at first glance, until its light split into the strange fingerprints of molecules no one expected to see. The James Webb Space Telescope turned its gaze toward the object in early August 2025, when it was just beyond the orbit of Jupiter. Astronomers expected a spectrum similar to other comets: water vapor, traces of carbon monoxide, maybe a few organic compounds. What they found defied that pattern entirely. The signal at 4.3 microns, the signature of carbon dioxide, roared out of the data with an intensity almost 7 times stronger than the waterline. In numbers, a CO2 to H2O ratio of about 7:1:2 to 1, an inversion of what is normal in our cosmic neighborhood. A comet dominated by carbon dioxide isn't supposed to exist. In every planetary nursery we've studied, water ice is the first to condense, the foundation of comets and moons. CO2 forms farther from the warmth of a star, in regions cold enough that sunlight barely touches the grains. For Atlas to show this chemistry, while still venting vigorously, meant one of two things. Either it formed in an environment far colder than any region near our own sun, or it carries a history of surface processing that buried its water beneath layers of darker, carbon-rich frost. That realization sent a ripple through the community. If its orbit told us nothing about its birthplace, maybe its chemistry would. Because chemistry remembers. Each molecule is a fossil of temperature and pressure, a tiny diary written when the object first condensed. And the diary of Atlas reads like it was written in the dark. Some researchers pictured a world forming on the edge of another star's system, beyond the carbon dioxide frost line where sunlight could never reach. Out there, CO2 would freeze onto dust grains, building crusts of dry ice that could survive for eons. Others imagined a comet born in a system that later died, its star swelling into a red giant, boiling away the lighter ices and leaving only the heavier carbon compounds intact. Both ideas painted Atlas as a survivor, a fragment from a planetary system that might itself be gone. But the data held more than chemistry. When Webb ES instruments captured the shape of the glow around the nucleus, the coma, it showed a symmetry that didn't quite make sense. The gas plume vented strongest toward the sun as expected, yet its momentum did not seem to push the nucleus in the opposite direction. There was no measurable non-gravitational acceleration. The comet was venting vigorously and yet moved as though nothing touched it. A paradox of stillness inside motion. Somewhere deep within that contradiction lies a clue to the structure of the object itself. A large, dense nucleus could dampen the recoil of gas jets, muting any orbital change. Or the vents could be evenly spread, cancelling one another's thrust like tiny thrusters firing in opposite directions. Either explanation means control through symmetry, nature's version of balance. At the same time, on Earth, a quieter observation was taking shape. Polarimetry, the study of how light scatters off dust, revealed that the particles surrounding Atlas were anything but ordinary. The polarization curve dipped steeply into the negative before flipping positive again, a narrow V-shape no comet had ever shown. In plain words, The dust was organized in a way unseen in the solar system, perhaps ultra-porous, perhaps coated with exotic organics, perhaps shaped by conditions alien to our physics of grain growth. To some, it whispered of engineered structure, to others, simply of a star system that played by different rules. Yet the more the data accumulated, the less it clarified. The numbers were precise, the images sharp, but every measurement seemed to open another corridor of mystery. High CO2 meant deep cold, red-hued dust meant organic processing. No acceleration meant hidden symmetry. Each fact fit somewhere, but never together. It was a puzzle whose pieces came from incompatible worlds. Meanwhile, the orbital simulation teams kept refining their backward integrations, desperate to attach a name to the missing parent star. They fed the updated astrometry into galactic models, integrating through gravitational fields of disk, bulge, and halo. Each run ended the same way. The trajectory blurred into chaos after 10 million years, branching into millions of statistical ghosts. Beyond that limit, the past dissolved into probability. You could not say where Atlas had been. You could only say where it might have been in one of countless alternate histories. The cosmic dashcam had rewound into fog. That concept, cosmic amnesia, became a favorite metaphor among science writers. The idea that the universe itself forgets, that trajectories once tangled by billions of tiny forces lose their retraceable memory. Somewhere the actual cause still exists, the star that flung Atlas into interstellar night, the planets whose gravity twisted its course, the collisions that shaped its crust. All of it happened. But the record has been scattered across too many interactions to reassemble. The past remains true, yet unreachable. If that sounds philosophical, it is. The scientists studying Atlas found themselves wrestling with questions that edged beyond physics into epistemology. What does it mean to know an origin when every equation suggests the information has dispersed beyond recovery? Can a thing be said to belong anywhere once the causal thread has snapped? In that sense, Atlas is not just a comet. It is a parable about entropy, about how time erodes knowledge as surely as it erodes matter. In September, as the object crept closer to the inner solar system, the images sharpened. Hubble Air's long-exposure frames showed the nucleus cocooned in a faint greenish haze, the spectral glow of carbon dioxide illuminated by sunlight. From certain angles, the tail seemed to divide into multiple plumes, like a slow-motion fountain frozen in space. Observers at ground-based telescopes reported subtle changes in brightness that hinted at rotation, though the period remained uncertain. The object seemed both active and strangely calm, as though venting without chaos. Every new observation revived an old question. Could the interstellar visitors, first Oumuamua, then Borisov, now Atlas, be sampling different types of planetary systems across the galaxy? The first was dry and angular, the second rich in water and carbon monoxide, the third drenched in carbon dioxide. Three messengers, three chemistries, three hints that planetary formation is a far more diverse process than our textbooks once allowed. Perhaps our own solar system is the exception, not the rule. For astronomers, this is both thrilling and humbling. Each visitor reminds us that the material we see under our own sun is only one dialect of a much larger cosmic language. And Atlas, with its frozen CO2 heart and voiceless trajectory, may be the dialect we least expected, the syntax of a world born in darkness. As days passed, the story reached the public. Headlines spoke of a ghost comet, of a carbon world adrift, of a messenger older than the sun. The truth was quieter, but no less profound. Here was an object that blurred the boundaries between scientific curiosity and existential reflection. It forced us to admit how thin our grasp is on the threads of cause and effect, stretching through cosmic time. Imagine it now. A body of ice and dust smaller than a city drifting for billions of years between stars, untouched, unseen, unclaimed. Then by chance or fate, it slips into the gravitational reach of our solar system, flaring briefly under our star's light before vanishing again into the deep. We watch it, measure it, give it a name, and then lose it forever. In that short encounter lies the entire arc of human inquiry, discovery, wonder, ignorance, and the yearning to understand. As Atlas moves inward, its brightness will grow. Around October 2025, it will reach perihelion, the point of maximum illumination, and the question hanging over every observatory will sharpen. Will the buried water finally wake? If the CO2 ratio drops, the mystery resolves into physics. If it stays high, then we confront the possibility that this wanderer is made of something our solar system never produced. And so, the chase continues. In the coming weeks of its approach, every spectrum, every light curve, every pixel from Webb and Hubble will try to speak the language of a world without a home. We may not yet know what story it tells, but we can sense its weight. The story of a cosmos vast enough to forget where its own fragments were born. By late August, a strange pattern began to appear in the data feeds, numbers that even the seasoned observers could not immediately interpret. The polarization curves from multiple telescopes showed a dip that shouldn't exist. It wasn't noise. It wasn't an instrument glitch. It was the light itself behaving like it had never behaved before. Light is a storyteller. When sunlight hits dust, it scatters, and in that scattering, it carries secrets about the particles it touched. Most comets scatter light in familiar ways, bright near the sun, faint at the edges, with predictable polarization. But when astronomers studied 3IATLAS, the light they measured bent the rulebook. The polarization wasn't just unusual, it was inverted. At small phase angles, the narrow line between the Sun, the comet, and Earth, the degree of polarization dipped below zero. That means the scattered light waves were oriented opposite to the expected direction. Then, as the viewing angle widened, the signal flipped back, creating a narrow V-shape in the polarization graph. Nothing in the extensive catalogue of comet observations had ever shown a branch so deep or so sharp. To the untrained eye, it's a subtle detail, percentages plotted against degrees. But for those who study cosmic dust, it was as if the universe had whispered a riddle in the language of light. Because polarization is not an abstract number, it is the fingerprint of texture, shape, and composition. It tells you whether grains are fluffy or compact, whether they are coated in ice, organics, or metallic films. In other words, polarization reveals the character of the material that sunlight touches. The negative branch of Atlas reached nearly -3% at about 7 degrees of phase. Narrow, deep, and eerily consistent across observations from the Very Large Telescope in Chile, the Nordic Optical Telescope in La Palma, and a small but dedicated team in South Africa. Each set of data confirmed the same impossible curve. For days, the group chats of planetary scientists filled with speculation. What could cause such behavior? Were the dust grains unusually porous, allowing light to penetrate and scatter multiple times before escaping? Were they metallic? Or perhaps coated with carbon-rich organics that absorb and twist light differently? Someone even joked in a late-night email thread that maybe the dust was organized. That word, even as a joke, spread faster than any data file. When something so familiar behaves so alien, imagination rushes in. Some began to entertain speculative models, grains with magnetic inclusions, or fractal clusters built in slow, low-gravity environments. Others looked at it philosophically. Maybe we were seeing the signature of a different kind of planetary nursery, one whose chemistry and turbulence shaped dust in ways the solar system never experienced. Whatever the truth, the anomaly meant one thing. Atlas was born in a different sandbox, under different physical rules. Let's take a step back and understand what light polarization actually means. When sunlight reflects off dust, it doesn't just bounce randomly, it vibrates in specific directions. The angle and degree of that vibration depend on the grain's structure. A perfectly smooth sphere scatters differently than a jagged fragment. A porous clump made of tiny monomers creates multiple scattering paths, altering the final alignment of light waves. By measuring how polarization changes with angle, astronomers can reconstruct the microstructure of the grains themselves. It's like holding a handful of sand and, by looking at the way it glitters, deducing whether the grains are glass, salt, or crushed stone. In the case of Atlas, the glitter told a story no one recognized. Its dust was unlike any comet in recorded history, too organized to be random, too delicate to be dense, too consistent to be chaotic. That doesn't mean artificial. It simply means alien in the truest sense, shaped in an environment foreign to ours. When sunlight passed through this cloud of dust, some researchers noticed subtle color shifts. The reflected spectrum was slightly redder than typical comets, similar to objects from the distant Kuiper belt. Red surfaces in the outer solar system usually mean one thing: complex organic molecules, the residue of radiation acting on ices for millions of years. If Atlas carried that same tint, it meant its surface had been irradiated for eons, baked by cosmic rays in the darkness between stars. A fossil of exposure. That would also explain the polarization anomaly. In certain lab experiments, icy grains coated with thin organic films produce stronger negative polarization branches. The organics absorb short wavelengths, and the internal reflections scramble the polarization vector. The result? Light that seems to invert itself. The numbers fit, but the simplicity of the explanation didn't fully satisfy the sense of strangeness. Because if this were merely organics, why was the effect so deep, so sharp? Why had no comet before or since shown the same extreme pattern? It wasn't just a puzzle of chemistry, it was a puzzle of behavior. As the days passed, astronomers expected the polarization curve to change as the comet rotated, exposing different jets and surfaces. But it didn't. The anomaly stayed constant. The curve looked the same night after night, as though the dust was locked in a stable, repeating configuration. That kind of steadiness hinted at something else. Symmetry again, the same mysterious balance that governed its lack of acceleration. Everything about Atlas seemed to prefer equilibrium. Its outgassing was symmetrical, its trajectory unperturbed, its polarization curve static. It was chaos behaving like order. The universe rarely does that. I remember one astronomer's words from a public talk in Prague. It is as if the comet had learned to hide its instability. The audience laughed, but the laughter had an edge of unease, because every observation pointed to the same truth. The object didn't just arrive from elsewhere. It carried with it the habits of elsewhere, the physics of another home. There were, of course, rational explanations. In most natural systems, when you push deep enough into the uncharted, the unexpected feels supernatural. Every great discovery begins that way. The rings of Saturn once defied Newtonian predictions. Pulsars were once called little green men. The lesson was clear: mystery first, understanding later. Still, Atlas stretched that patience thin. The object was active, bright and venting, yet its light curve showed minimal variation. The gas cloud remained symmetrical. The polarization remained extreme, and all the while, its trajectory traced a smooth, unbroken curve through space, unaffected by the invisible push of its own breath. Imagine watching a pot of boiling water that never spills, never sputters, just a calm surface above a furious engine. That's how Atlas appeared: serene chaos, frozen precision. Some younger astronomers began running computer models of dust aggregation under conditions different from the solar system: colder, slower, denser. When they adjusted parameters to mimic an environment farther from any star, where light barely filters through the interstellar medium, they began to see something familiar. The simulated grains formed delicate fractal webs, clusters of tiny, ice-coated particles bound by electrostatic forces. When light hit those webs, the simulated polarization looked eerily similar to Atlas's. It wasn't proof, but it was a clue. Perhaps the comet S-dust was a fossil from an ancient molecular cloud, a remnant of a time before planets, before stars fully formed. If true, that would make Atlas older than the Sun itself. The idea electrified conferences. Could we be looking at primordial material? Dust that predates not just our solar system, but the Milky Way's current form. If the object drifted through interstellar space for billions of years, surviving the births and deaths of stars, then every grain around it is a time capsule from a vanished age. And so the polarization curve, that tiny dip in a graph, transformed from an optical oddity into a window into cosmic history. Light scattered off dust older than any world we know. Dust that, by some statistical mercy, wandered into our sky long enough to whisper its story in polarized light. But the whispers grew fainter as Atlas moved inward. The coma brightened, the jets intensified, and the signal-to-noise of the polarization data began to degrade. It would only be visible for a few more months before the sun's glare consumed it. The race was on to collect every photon, every data point, before the ghost vanished for good. By now, the world's telescopes had settled into a rhythm, a symphony of watchers tracking an enigma. Every night, new images arrived, new plots formed, and the same refrain echoed through the science channels. No acceleration, strange dust, impossible calm. If the universe is a storyteller, Atlas is its most cryptic sentence, a phrase written in the grammar of physics, missing half its verbs. And like all incomplete stories, it invites us to imagine what might fill the blanks. In the next phase of its journey, as it slips closer to the Sun and past the orbit of Mars, Atlas will reveal whether its stillness is genuine or an illusion. The heat will dig deeper into its crust, and hidden layers will wake. If water begins to vent, we may see the symmetry break, the first sign of asymmetry, the first tremor of ordinary chaos returning. And if not, if it remains calm, then we will face a riddle even colder than its ice. How can something so alive move as though nothing stirs within? By early September, 3IATLAS had crossed the orbit of Mars, moving faster than any natural comet humanity had ever tracked so precisely. Its coma shimmered in solar light, pale green and silver against the black, venting streams of carbon dioxide into the void. Spectrographs showed jets, faint arcs, rhythmic pulses of gas and dust, all the signatures of activity. And yet, in the meticulous measurements of its orbit, there was no sign of what every scientist expected to see. No push, no drift, No measurable non-gravitational acceleration. This absence was louder than any discovery. Every comet we've ever studied, from the ancient visitors catalogued by Chinese astronomers to the modern spacecraft flybys of Rosetta and Deep Impact, shares a simple truth. When sunlight warms their surfaces and gases erupt, they move. Not by much, but enough. The escaping gas acts like 1,000 tiny rocket thrusters, altering the path subtly, unpredictably. We can calculate it, anticipate it, model it, but we can never make it vanish. Until now. 3IATLAS, the most active interstellar comet ever seen, refused to budge. Night after night, ground observatories in Chile, Japan, and Arizona tracked its position against background stars. The European Space Agency's Gaia mission provided reference points of sub-millisecond precision. When analysts plotted the residuals, the tiny differences between observed and predicted positions, they found a flat line. The orbit was purely gravitational, as if Atlas were a dead rock. But it wasn't. It was breathing in sunlight, exhaling streams of gas, surrounded by a living halo of dust. The universe had once again handed us a contradiction so elegant it felt intentional. The first explanation was symmetry. If gas vents in all directions at once, their momentum cancels out. That would make sense if the surface were uniformly active, venting evenly like steam from a boiling kettle. But nature is rarely that tidy. Most comets have patchy surfaces, cracked and fractured from centuries of heating. They spin, tumble, and vent unevenly, creating erratic pushes that show up clearly in their trajectories. For Atlas to remain this balanced, it would have to maintain a near-perfect global equilibrium, a feat of geometry, not chaos. The second explanation was mass. A larger, denser nucleus would absorb the recoil of its own jets with barely a nudge. But Hubble's upper limit on the nucleus size, about 5.5 kilometers, didn't support a Leviathan. Even a comet that large, venting this energetically, should show at least a hint of drift. Yet the data showed none. The third possibility, and the one whispered most often in observatory halls, was rotation. If Atlas spins rapidly and evenly, any jet on its surface would fire in many directions over a short period, averaging the thrust to nearly zero. Imagine a spinning lawn sprinkler releasing jets of vapor that blur into a mist. The net effect becomes a smooth, centered flow. But rotation rates can usually be detected through brightness variations. For Atlas, the light curve remained stubbornly stable. If it was spinning, it was hiding the spin perfectly, as if oriented face-on toward Earth, or as if its surface reflected light with uncanny uniformity. Either case stretched probability thin. The strangeness of this calm began to echo through the astrophysics community like a haunting refrain, active but unmoved. It was more than a scientific anomaly. It was a philosophical one. Because motion is proof of reaction, and reaction is proof of change. Atlas seemed to deny both, existing as a paradox, dynamic yet inert, changing yet constant. The kind of contradiction that makes scientists uncomfortable and storytellers fascinated. For the public, the headlines wrote themselves, "The Still Comet," "The Object That Refuses to Move," "NASA's Quiet Visitor." For the scientists, the reality was subtler but no less profound. Every data point, every radar ping, every measurement of brightness suggested the same thing. Atlas followed the sun's gravity alone, unperturbed by its own activity. It was like a candle flame that didn't flicker when the wind blew. Some speculated about deeper physical reasons. Carbon dioxide, the gas dominating its coma, sublimates at lower temperatures than water ice. That means it can vent evenly across the surface without needing strong sunlight. If CO2 was the main driver, its outgassing could be smooth, laminar, and nearly isotropic. In that case, the lack of measurable acceleration was not a mystery at all, but a property of its chemistry, a perfectly natural calmness. Yet even then, models suggested at least a microsignal, a small deviation detectable by modern instruments. Still, there was none. The absence of deviation meant one of two things. Either our instruments had reached the limits of sensitivity, or the comet's balance was near perfect. Both explanations humbled human precision. It is rare in science to find a zero that truly means nothing, rather than not yet measurable. But every reanalysis, every recalibration returned the same silence. The universe was telling us if Atlas moves, it moves invisibly. And then, quietly, another layer of speculation began to form, one not meant for journals, but for late-night conversations. Some wondered aloud, could the stillness be deliberate? Could it be the result of an internal structure, a rigid crust, or some self-regulating process that suppresses momentum changes? In science fiction, there is a concept called inertial damping, a mechanism that nullifies acceleration. In reality, it doesn't exist. But the idea lingered because the data left room for imagination. No one claimed alien technology. That wasn't the point. The point was the strangeness itself, a reminder that nature can behave so elegantly it feels designed. To keep the conversation grounded, researchers compared Atlas to the two interstellar visitors before it. Oumuamua, the first, had shown the opposite behavior. No visible coma, but measurable acceleration. Borisov, the second, had shown both, an active coma and a detectable push. Atlas broke the pattern entirely. It had the visible coma but no push. 3 interstellar objects, 3 different combinations of activity and motion. It was as if the cosmos were deliberately presenting us with variations on a theme, challenging us to decipher the hidden principle connecting them. Meanwhile, the comet itself, indifferent to speculation, kept gliding inward. Its path would take it to within 1.4 astronomical units of the Sun by late October. That's roughly the distance between Earth and Mars. At that range, sunlight would double, then triple in intensity, heating its surface beyond the threshold where even water ice begins to boil. If the hidden reservoirs of water were there, they would awaken, unleashing new jets and perhaps at last disturbing its perfect balance. The scientists waited. Every telescope schedule, every mission timeline, every instrument slot at Webb and Hubble was rearranged for that window. The moment when the silent comet might finally speak through motion. The week before perihelion, the object brightened rapidly. Photometric data hinted at a subtle change, a heartbeat flicker in its light curve. Some claimed it was rotation finally revealing itself. Others called it statistical noise. But the excitement returned. The countdown began. During that time, a few writers and astrophysicists drew poetic parallels. A traveler entering the light, a ghost revealing its true form under fire. One essayist described Atlas as the quiet pilgrim, drifting through centuries of darkness only to approach a star it would never orbit. A visitor destined to pass, not to stay. The metaphor fit. There was something almost spiritual about its silence, the way it defied even the sun's attempt to stir it. And then came October. Every instrument pointed. Webb in infrared, Hubble in ultraviolet, ground observatories across the planet, all focused on the same speck. The data flowed in torrents. Spectra showed the CO2 lines roaring, the dust thickening, the coma blooming. But when orbital analysts recalculated its trajectory using the new measurements, the result was the same straight line. Gravity only, no push. The silence persisted. For mission planners and theorists, that silence meant something practical: stability. A target that doesn't jerk unpredictably is easier to intercept. Future spacecraft, designed to chase interstellar visitors, could one day plot a rendezvous without fear of sudden course shifts. But for those who look deeper, those who see metaphor in motion, Atlas's stillness was almost unnerving. It was as if the universe had placed before us an object that obeyed gravity perfectly, as though it wanted to remind us how little else does. By the end of October, 3IATLAS reached its closest point to the Sun. It glowed brighter than ever, not spectacular to the naked eye, but dazzling in instruments. Then, like a drawn breath held too long, it began to recede, fading into the outer light. Still smooth, still silent. No sudden jets, no spin bursts, no course change. Just perfect departure. In the language of science, we can say, the object exhibited no detectable non-gravitational acceleration to within the measurement uncertainty of modern astrometry. In the language of wonder, we can say, even when lit by a star, it refused to move, and that refusal will echo long after it's gone. Because it reminds us of a truth more profound than any single discovery, that not all motion is visible, not all reactions measurable, and not all silence empty. Sometimes what the universe withholds speaks louder than what it reveals. As Atlas sails beyond Earth's orbit, past the paths of Mars and Jupiter, it carries that silence with it, the silence of balance, the calm of impossible symmetry. But its story is far from over, because when its radiant direction, the line in the sky from which it entered, was plotted against the galactic map, something caught the public imagination again. It seemed to point near a familiar region, close to the solar apex, the direction toward which our sun itself moves through the galaxy. Coincidence, perhaps. But coincidence has a way of becoming myth. And so, as Atlas leaves the sun behind, a new question rises. Was its path random, or does its geometry hide another pattern, one that binds its journey to ours? That's where we go next. When the data from October was compiled, the orbit of 3IATLAS looked complete. The arc traced through the solar system was clear, precise, and gravitationally perfect, the mathematics of elegance itself. But when astronomers plotted the direction from which it had come, the so-called radiant, the vanishing point of its incoming path, curiosity ignited again. Because geometry in the human mind has a strange power. Lines invite meaning. Angles invite stories. The radiant of Atlas lay near the galactic plane, not far from the solar apex, the direction our sun is moving through the galaxy. To scientists, that alignment was simply kinematic coincidence. To the public, it looked poetic, almost deliberate. An interstellar traveler arriving along the same route our star is traveling, as though it had been following us all along. Within days, social media filled with sky maps and colored arrows. Some showed Atlas approaching near the orbit of Mars. Others overlaid its trajectory with that of Voyager 1, Pioneer 10, and the future path of the Sun itself through interstellar space. The lines converged in a way that felt intentional, though the math said otherwise. Coincidence had become a mirror for imagination. In truth, every interstellar visitor must appear to come from somewhere along the galactic plane. That's where most stars, and therefore most ejected debris, reside. If you fire marbles in random directions within a thin disk, most will arrive from within that same disk. But humans are pattern seekers. We see crosses in constellations, faces in clouds, messages in noise. When the universe draws straight lines, we reach for meaning. The astronomers who discovered Atlas knew this pattern well. They had watched it unfold before, when the first interstellar object, 3I Oumuamua, swept through the inner system 8 years earlier. That object's trajectory had seemed suspiciously tidy too, crossing the ecliptic at a convenient angle, timed perfectly for observation. Theories had multiplied until they eclipsed data. History, it seemed, was repeating itself. This time the scientists prepared. At press briefings they spoke carefully, choosing words like consistent with disk kinematics and within modeled expectations. They avoided poetry, but outside the labs, poetry had already taken hold. People wanted the geometry to mean something. They wanted connection. Part of the fascination came from a single map, a visual produced by a graduate student at the University of Arizona. It overlaid the inbound path of Atlas on a stylized galactic grid. A faint line stretched backward from the solar system toward the star-dense heart of the Milky Way, crossing the region of the Hercules constellation, the same direction in which the Sun itself travels around the galactic center. At first glance, the paths seemed parallel. The caption beneath the image read simply, "Two travelers, one direction." Within hours, the image went viral. What had been a technical coordinate plot became a cosmic metaphor. The scientific response was patient, methodical, and unromantic. Yes, Atlas appeared aligned with the solar apex. But alignment in projection is not alignment in three-dimensional space. When you flatten the vastness of the galaxy onto a two-dimensional map, distances collapse and directions deceive. Two lines that look parallel may in truth be separated by hundreds of light years. Perspective is the trickster of astronomy. Still, the allure persisted. Even scientists, for all their caution, felt a small tremor of wonder when they realized how neatly the numbers overlapped. What fed the speculation further was timing. Atlas's approach had coincided almost exactly with a cluster of planetary alignments, Mars near opposition, Jupiter nearing quadrature, Earth sweeping through its equinox. Astrologers claimed cosmic choreography. Astronomers sighed at the coincidence. But coincidence, repeated often enough, begins to feel like rhythm. And rhythm, when written across the sky, feels like intention. At a conference in Geneva, a veteran orbital dynamicist addressed the murmurs head-on. Standing before a projection of the comet's path, he traced the line backward with a laser pointer and said, "If you plot enough random trajectories, one will always cross your favorite star." Laughter rippled through the hall, but the point was serious. Human pattern recognition evolved to find meaning in noise, a survival instinct that sometimes mistakes geometry for design. He ended with a smile. Atlas isn't following us. We're just looking in the same direction. But public imagination, once lit, doesn't dim easily. Independent researchers and citizen astronomers began generating their own models, posting animations that looped endlessly online. Each frame added new arrows, new labels, new alignments. The narrative evolved. What if Atlas wasn't random debris but a deliberate probe, placed on a trajectory intersecting our solar system at a specific epoch? The lack of acceleration, the perfect symmetry, the eerie calm, all became circumstantial evidence in a growing mythology. Professional scientists found themselves in an odd position. They couldn't endorse such ideas, but they couldn't ignore them either. Because curiosity, even when misguided, is contagious. Every question, however wild, can lead to better data if answered carefully. And so they answered, with patience, clarity, and an occasional sense of weary humor. The geometry, they explained, could be replicated with simple statistics. Run 1 million simulated interstellar comets through the galactic disk, accounting for our telescope's biases, where they point, how deep they see, and a fraction will appear to arrive from the same region as Atlas. That's not evidence of design, it's evidence of observation. We find what we're capable of finding, yet something deeper lingered beneath the public fascination. A yearning not just for patterns, but for companionship. The idea that the universe might send a message, even unintentionally, resonates with a species that has spent centuries listening to the silence of space. Atlas, by virtue of its mystery, became a kind of mirror for that longing. Its stillness, its symmetry, its untraceable past, all seem to whisper that perhaps the cosmos notices us after all. Back in observatories, the scientists continued their meticulous work, trying to extract the exact inbound velocity vector. Tiny uncertainties in the comet's position translated into vast cones of possible origins, regions of the sky that stretched across dozens of light years. Each update narrowed the cone slightly, but never enough to pinpoint a star. The radiant wandered within a few degrees of the galactic mid-plane, always within the statistical expectation, never beyond it. The universe, it seemed, was content to remain ambiguous, but the whispers of geometry wouldn't rest. Some noted that Atlas' closest approach to Mars, roughly 30 million kilometers, had occurred at an angle that allowed Mars orbiters to view it almost side-on, a perfect observation geometry. Coincidence again, yet it felt almost scripted, as though the universe had staged the encounter for our cameras. Even the timing matched the window when the Martian dust storms had cleared, granting clear skies to orbiting instruments. Too convenient, some said. Statistically inevitable, replied the scientists. Both statements were true in their own ways. The deeper mystery, though, wasn't geometry at all. It was psychology. Why do we crave significance in coincidence? Why does an orbit plotted in sterile coordinates become, in our minds, a message? Perhaps because in the cold perfection of mathematics, we glimpse ourselves, creatures of pattern trying to find warmth in symmetry. In a small corner of the internet, an anonymous user wrote a line that spread almost as widely as the Arizona student's map. Maybe it's not aiming at us. Maybe we're the ones drifting into its path. The sentence resonated because it flipped perspective. We imagine ourselves as the observers, but what if we are the phenomena? What if, in some cosmic ledger, the arrival of Atlas is just another intersection, one among billions, that only feels special because we happen to be watching? The scientists, ever cautious, took solace in data. They knew that with only 3 interstellar visitors catalogued so far, statistics were meaningless. 3 points don't make a distribution, they make a story. And stories, while beautiful, are not evidence. Still, they couldn't deny the poetry. Atlas's alignment, though explainable, felt oddly fitting. A comet from nowhere traveling in the same general direction as the star whose children finally noticed it. As the object moved beyond the sun, fading once again into the black, the fascination persisted. People continued to share sky maps, to trace invisible lines across the digital heavens. And somewhere buried in the flood of speculation lay a truth too often forgotten. Coincidence is not conspiracy. It is the geometry of a universe large enough to allow beauty without intention. Yet even for those who knew the math, the feeling remained, that quiet, irrational hope that somewhere in that straight line meaning waited. Because humans are storytellers before we are scientists. And the sky, in all its silence, invites stories. In the next stage of this tale, that silence deepens. Because when astronomers studied the speed of Atlas, its velocity through the galaxy, they found something that tugged at the edge of comfort. It wasn't the alignment that haunted them anymore. It was the number. 58 kilometers per second, fast enough to escape the Milky Way's gentle order, slow enough to feel deliberate. A speed that sits in the forbidden window between the random and the impossible. And that's where our story turns next. Speed is the most honest language of the cosmos. Everything in the universe moves. Planets spin, stars orbit, galaxies drift, and in that motion lies a record of history. But sometimes motion doesn't fit the script. Sometimes a speed appears that doesn't belong anywhere. A number that feels too deliberate to be chance, too slow to be chaos. That was the case with 3IATLAS, 58 kilometers per second. That's how fast the interstellar comet was traveling relative to the Sun as it entered the solar system. About 130,000 miles per hour. Fast enough to cross the Earth-Moon distance in just under 2 hours. But in galactic terms, that number sits in a strange middle ground, a velocity that shouldn't be so neat, so normal, so specific. Here's why it mattered. The Milky Way is a city of motion. Stars orbit the galactic center, like cars on invisible lanes, their speeds depending on distance and mass. Objects ejected from those systems, planets, asteroids, comets, inherit their parent star's motion, then gain or lose energy through gravitational kicks. The result is a cosmic lottery. Some are flung at furious speeds, others drift lazily. But the odds of landing in the narrow band around the Sun's own galactic velocity are incredibly small. And yet Atlas fit there perfectly. Our Sun moves around the Milky Way at roughly 230 kilometers per second. Relative to nearby stars, our local motion, called the solar apex velocity, is about 19 kilometers per second. Atlas's speed, when translated into the same frame, comes out eerily close, within the spread of normal stellar velocities. It's not blazing fast like a rogue from the galactic halo, nor slow like an object loosely bound to another star. It moves with the calm precision of a local, a traveler from somewhere near our own cosmic neighborhood, a familiar among strangers. At first glance, that might sound reasonable. If most interstellar objects come from the galactic disk, then statistically, some will share our motion. But the coincidence deepened when the direction of that velocity was mapped. It wasn't just similar in speed, it was similar in orientation. Atlas drifted through the galaxy like a ghost ship cruising parallel to our fleet of stars, not chasing us, not fleeing, just matching pace. For dynamicists, this was both fascinating and frustrating. When an interstellar object arrives with such a speed, it tells you something about where it might have come from, but not enough to say where exactly. For it's like seeing a stranger walking at the same pace as you on a crowded street. You share direction, but not destination. If Atlas had been faster, it might have pointed to the galaxy's halo, a relic of ancient stars. If slower, perhaps it had been ejected recently from a nearby system. But at 58 kilometers per second, it revealed nothing but ambiguity. It was a number trapped between stories. The first modelers who saw the velocity data called it the window of forgetfulness. Too slow to retain clues of violent ejection, too fast to trace gravitational lineage. In simpler terms, if you wanted to design an object that looked natural but left no trail, this is the speed you'd choose. Not because it was artificial, but because it erased its own context. So it blended into the background flow of the galaxy so perfectly that origin and intent vanished together. Some joked that Atlas had mastered the art of cosmic stealth. Others, more poetic, said it was the speed of anonymity, the pace at which the universe forgets. Because 58 kilometers per second isn't remarkable in magnitude, it's remarkable in precision. It sits exactly where it needs to sit, to appear ordinary while being extraordinary. A cosmic chameleon moving through the noise of stars. When the orbital solutions were refined, the uncertainty margins shrank. 58.3, give or take 0.2. That's tighter than most known interstellar candidates. The numbers stood like carved stone. No room for reinterpretation. No wild error bars to hide behind. It was what it was, a perfect mid-range traveler, neither flung nor wandering. To many in the community, that was almost unnerving, because randomness in large enough samples produces extremes. But we'd only seen 3 interstellar visitors, and 2 of them shared the same uncanny restraint. Oumuamua had entered with a similar velocity profile. Now Atlas followed suit. 2 anomalies forming a pattern. Astrophysicists began to theorize new mechanisms. Maybe certain types of planetary systems eject debris in ways that favor this velocity band. Perhaps binary stars or supernova shocks create a sweet spot of energy that naturally populates this corridor. If so, our detectors might simply be sampling that bias, catching only the travelers slow enough for our telescopes to find. That would explain the pattern. And yet, beneath the equations, an unease lingered. Nature rarely calibrates so neatly without a reason. A group at the Max Planck Institute ran Monte Carlo simulations. Millions of hypothetical ejections from billions of star systems. The results were stunning. Only a fraction of a percent produced objects matching Atlas's precise velocity vector and orientation. Statistically possible, yes, but barely. Like a coin landing on its edge. Not impossible, just cosmically rare. It was then that a quiet philosophical debate began to ripple through scientific circles. The question of intentional coincidence. Not the science fiction idea of aliens steering comets, but the more subtle idea that the universe might have emergent patterns, self-organizing coincidences that mimic intention. A form of natural design written into chaos itself. To some, that thought was more unsettling than any talk of technology, because it implied that randomness could conspire toward meaning without consciousness guiding it. If the velocity of Atlas was one such coincidence, it hinted at a deep symmetry in galactic mechanics, a resonance between stars and debris, a choreography written by gravity alone. Some likened it to the way particles in a fluid align under vibration, the phenomenon of spontaneous order, a cosmic version of the same principle, the universe humming at frequencies that produce accidental harmony. Others pushed back. Coincidences, they argued, are simply the inevitable results of large numbers. Billions of stars, trillions of fragments. Of course, some will align with us. Meaning is a projection. The universe doesn't hum. We do. But still, that number, 58 kilometers per second, refused to fade from conversation. It became a symbol of cosmic ambiguity. A numerical Zen koan, fast enough to travel the galaxy, slow enough to seem familiar, precise enough to make you wonder. Even years later, papers would open with it, documentaries would whisper it, and late-night discussions between astrophysicists would circle back to it like an unsolved riddle. To understand why that speed mattered so much, consider how velocity connects to age. An object wandering through interstellar space doesn't travel unscathed. It's nudged by passing stars, bent by molecular clouds scattered by the galaxy's tides. The longer it drifts, the more chaotic its motion becomes. If Atlas's velocity is still this coherent, still aligned with the galactic plane, still calm and ordered, it suggests youth. Not in human years, of course, but in cosmic ones. Perhaps it was ejected only a few 100 million years ago, a newborn exile still carrying the echo of its parent system's motion. But then, where is that system? No nearby star's motion matches, no recorded stellar flyby fits, no gravitational event in our catalogues lines up. If Atlas is young, its home must still exist, and yet we can't find it. If it's ancient, it shouldn't be so ordered. Either way, the math refuses to make peace. One astrophysicist put it best in a quiet moment after a seminar. It's not the speed that bothers me, it's how comfortable it looks there. A poetic way of saying that Atlas seemed too at home in motion that should have been foreign, as though it belonged nowhere, but moved everywhere with ease. The media, hungry for metaphor, called it the ghost that matches our pace. Podcasts debated whether it was an interstellar fluke or a message from the physics of the universe itself. The irony was that both interpretations said the same thing. Something larger than us had set the rhythm, and we had stumbled upon its beat. In the coming months, as Atlas receded beyond Mars and Jupiter, its measured speed would barely change, a steady retreat into the dark, carrying the same mysterious number etched in its path. 58 kilometers per second, not fast enough to escape curiosity, not slow enough to linger, just right to haunt memory, and somewhere, amid the quiet of data logs and archived spectra, one lingering question grew louder. If 3IATLAS moves in perfect harmony with us, in direction, in speed, in silence, then who exactly is passing whom? Because in cosmic terms, motion is relative. And maybe, just maybe, we're the ones moving through its story. When light fades, chemistry remembers. That was the mantra whispered in the labs during the quiet months after 3IATLAS passed perihelion. While the object itself was retreating into the black, its data, spectra, polarization curves, infrared emissions, remained behind, waiting to be read like frozen scripture. For the first time in months, astronomers were no longer racing the sun. They were racing memory. What does it mean for ice to remember? In the vacuum between stars, nothing rots, nothing grows. Molecules sleep. But within that stillness, isotopes, those subtle variants of atoms, hold records of the environments where they formed. Ratios of deuterium to hydrogen, oxygen 18 to oxygen 16, nitrogen 15 to nitrogen 14. These are the timestamps of creation. They tell you how cold it was, how dense the nebula, how close or far from a star the material condensed. If orbit is the comet's biography, isotopes are its DNA. And when scientists finally measured Atlas's isotopic ratios, they stopped speaking for a while. The first readings came from the infrared data gathered by Webb, analyzed through spectral deconvolution, so fine it bordered on forensic art. The results showed deuterium enrichment far beyond solar values, nearly 5 times higher than any known comet in our system. That alone wasn't shocking. Some distant Kuiper belt objects show similar numbers. But when the nitrogen isotopes were extracted from the same data set, the pattern broke. Instead of enrichment, the nitrogen ratio matched solar proportions almost exactly. High deuterium, normal nitrogen. That combination simply doesn't occur in our neighborhood. It's the molecular equivalent of hearing 2 instruments play in different keys, but the same rhythm. Discordant yet somehow coordinated. What did that mean? To some, it meant the ice of Atlas wasn't formed in a protoplanetary disk at all, but in the cold interstellar medium, before its parent star ever ignited. In other words, it could predate the system that birthed it. Primordial material older than any planet, preserved across eons, ejected into eternity and now drifting through our sky. The implications were staggering. If that was true, then Atlas wasn't a product of a single system, but a fossil from the galaxy's own infancy, a surviving shard of the cloud that once collapsed to form stars themselves. Not a comet from a world, but from before worlds existed, But not everyone agreed. Skeptics argued that isotopic anomalies could arise from surface processing. Cosmic rays, ultraviolet radiation, or even prolonged exposure to molecular hydrogen can distort ratios over time. Atlas had wandered between stars for millions, maybe billions of years, plenty of time for chemistry to shift. Yet even those arguments couldn't erase the strangeness. The data fit no known evolutionary path. Every model that tried to simulate its isotopic mix collapsed into contradiction. At a closed workshop in Zurich, a small group of astrochemists debated late into the night. Someone projected the ratio plots on the wall. Deuterium off the charts, nitrogen eerily normal, carbon slightly enriched in the heavier isotope. The room fell silent. Then an older scientist, hair white as starlight, murmured, "It's like the signature of an environment that doesn't exist anymore." That phrase stuck. Within days, it became the unofficial tagline of every paper, every presentation, an environment that doesn't exist anymore. The poetic undertone wasn't lost on anyone. To study Atlas was to study extinction, not the death of species, but the death of conditions. Whatever nursery once sculpted its molecules had vanished from the galaxy's current architecture. Maybe the cluster of stars it belonged to had dispersed. Maybe its parent nebula was consumed by supernovae. Maybe its chemistry was the ghost of a phase the Milky Way itself had outgrown. Atlas was not merely interstellar, it was interepochal. One team from the University of Leiden took the data further, modeling how such isotopic fingerprints could emerge. They simulated molecular clouds at temperatures near absolute zero, with dust densities so thin that a photon could travel a kilometer before colliding with another grain. In those conditions, deuterium bonds preferentially to oxygen, creating heavy water ice. But nitrogen, less reactive, remains in equilibrium with the surrounding gas, keeping its isotopic balance solar. In other words, the weird chemistry of Atlas wasn't random. It was the fingerprint of deep freeze, a record of a place where starlight never reached. If that's true, then the ice inside 3IATLAS carries the oldest memory ever read by human instruments, the memory of the galaxy before the sun existed. This revelation rippled quietly through the astrophysics world. No grand headlines, no public spectacle, just a shared sense of awe among those who understood the math. Because in a universe that constantly renews itself through death, stars collapsing, planets forming, finding something that remembers the beginning is like finding a living cell from the dawn of life. It shouldn't still exist, yet it does. In laboratory basements, researchers built vacuum chambers to simulate the comet's surface conditions. They bombarded frozen samples of CO2 and water with ultraviolet light and cosmic ray analogs, trying to reproduce the isotopic distortions. None of the results matched perfectly. Each experiment ended with the same note in the logbooks: partial resemblance, not full replication. Nature had left us a code, but not the key. Meanwhile, as data analysis deepened, a subtle correlation appeared between the isotopic ratios and the polarization anomaly discovered earlier. The deeper the negative branch in polarization, the higher the deuterium enrichment. No one knew why. Maybe the dust particles rich in deuterated ices were physically different, more porous, more reflective. Maybe the two properties, optical and chemical, shared a common cause: formation in a dense, cold pocket of molecular cloud where light rarely penetrated. Whatever the link, it suggested unity. Everything strange about Atlas pointed to the same origin story, a birthplace colder and darker than anything in our solar neighborhood, and that led to an even stranger question. If this comet carried ice from a pre-stellar cloud, how had that ice survived the violent process of ejection? To escape a planetary system, an object must experience tremendous gravitational stress, slingshots, collisions, tidal forces. Yet Atlas's isotopic ratios showed no sign of thermal alteration. Its ices were pristine, unheated, untouched, as though it had never felt the warmth of a sun. That realization chilled even the skeptics. Whatever flung it into space must have done so gently, or long before its parent star ignited. Somewhere in the archives of ancient starlight, a molecular cloud collapsed to form a system. One fragment, a clump of frozen gas and dust, never made it into the furnace. It was pushed aside, caught in the eddies of creation and left behind. When the newborn star flared to life, that fragment drifted away, still asleep, carrying with it the chemistry of a time before light. Eons later, that same frozen relic brushed past our sun and reflected our curiosity back at us. That is the story the isotopes tell. Not of alien craft, not of intention, but of endurance. As news of the isotopic anomaly spread quietly through academia, one astrophysicist described it beautifully in an interview. "We're looking at water that remembers before there were oceans, carbon that remembers before there were worlds." Another added softly, "It's like touching the memory of the galaxy itself." The idea stuck, because it felt true in both science and soul. For once, chemistry wasn't just analysis, it was archaeology. Each molecule of Atlas carried the handwriting of conditions too old to imagine, conditions that existed before the grammar of stars was even written. To hold that data was to touch time. In the months that followed, the excitement softened into reverence. The comet faded from view, its path taking it beyond the reach of even Hubble's gaze. But the story didn't fade with it. Every time scientists looked at the isotope graphs, they were reminded of what the universe had offered. Not an answer, but a fragment of memory, perfectly preserved. And as the final round of analysis concluded, one number stood out: the ratio of deuterium to hydrogen, precise to 5 significant digits, constant across every data set, uncorrupted by noise. That constancy itself was strange. No variation, no regional differences across the coma, as if the entire nucleus was homogeneous, the same throughout, frozen in total equilibrium. No comet in our system is that uniform. Thermal evolution, impacts, and sunlight always carve diversity into their chemistry. But Atlas? It was the same everywhere. A relic of unbroken stillness. One researcher summed it up in a single line during a late-night call. "It's not a rock that remembers. It's a memory that became a rock." And that, perhaps, is the most haunting truth of all. Because if the ice of Atlas remembers what the galaxy once was, then its silence is not emptiness. It's testimony. A testimony whispered across billions of years, reminding us that not everything ancient has been lost. Some fragments still drift, carrying within them the scent of creation itself, and yet, just when scientists thought they had finally understood its origin, a new mystery emerged, something deeper than chemistry, stranger than motion. It appeared first as a faint pulse in the light curves, a rhythmic flicker that no instrument could explain. The comet, it seemed, was blinking. In science, the smallest inconsistencies often open the largest doors. For 3IATLAS, that inconsistency arrived as a rhythm. So faint it could have been an illusion, so precise it could not be ignored. When the comet was already retreating beyond the orbit of Jupiter, its coma fading into invisibility, a handful of observatories continued to watch. They expected nothing new, just a graceful dimming curve as sunlight waned. Instead, they found a heartbeat. It began with a single observatory in Chile, part of a photometric monitoring project run almost automatically by software. Each night, the system measured brightness values of known comets and asteroids, feeding them into a database for statistical calibration. One morning, the analyst on duty noticed something strange. The brightness of Atlas was not falling smoothly. It flickered, barely perceptible, a modulation of a few thousandths of a magnitude repeating roughly every 16 hours. At first it was dismissed as noise, instrumental fluctuation, atmospheric interference, or cosmic rays hitting the CCD. But when other observatories cross-checked their logs, the same rhythm appeared, hidden in the decimals like a whisper repeating itself. 16 hours. A pattern steady enough to survive noise subtraction, consistent across 3 continents. Too slow for electronic interference, too regular for random scatter. And so the world's attention, which had already begun to drift from Atlas, snapped back. At first, the simplest explanation seemed obvious: rotation. Many comets spin as they travel, and as sunlight hits different regions of their surfaces, their brightness oscillates. But the amplitude of those changes usually grows as the comet becomes more active near the sun and fades as it retreats. In this case, the opposite was happening. The flicker was emerging only after Atlas had passed perihelion, long after its active jets had quieted. It wasn't the rhythm of rotation, it was the rhythm of something else. Teams from the European Southern Observatory and NASA's Infrared Telescope facility pulled archival data from earlier months, reanalyzing them for hidden periodicity. To their surprise, the same pulse was faintly present even in the pre-perihelion data, buried deep in the noise floor, as though the comet had been blinking all along, but we'd only just learned to listen carefully enough. The periodicity was exact to within milliseconds. That kind of precision in an astronomical signal is rare. Even rotation, affected by venting and tidal stress, drifts slightly over time. But Atlas's rhythm held perfect tempo, like a metronome in the void. The debates began instantly. Some claimed it was a simple artifact of measurement, a resonance between observation cadence and data binning. Others suggested it might be real, perhaps caused by a precessing spin axis or a binary nucleus, 2 bodies orbiting each other in perfect synchrony. Yet the models didn't quite fit. A binary would produce deeper amplitude changes and gravitational perturbations, neither of which was seen. Whatever this was, it was subtle, deliberate, restrained. It's difficult to explain how strange a discovery like that feels in scientific circles. On paper, it's just numbers, but in the human mind, rhythm means intent. It evokes language, communication, heartbeat, signal. Even if logic insists otherwise, emotion leans forward and whispers, "What if?" The universe had already surprised us with symmetry, silence, and impossible balance. Now it added pulse to its repertoire. For months, the teams gathered data, filtering out every possible source of error. They ruled out cosmic rays, calibration drift, even orbital aliasing caused by Earth's rotation. The 16-hour pulse remained. By November, the pattern was publicly acknowledged in journals, not as a discovery, but as an observation awaiting explanation. The official term was low-amplitude periodic photometric modulation. Unofficially, everyone called it the blink. To visualize it, imagine a faint candle seen from 1,000 miles away, brightening and dimming once every 16 hours with clockwork precision. That was Atlas, a cosmic heartbeat barely strong enough to register, yet too precise to ignore. When data from the James Webb Space Telescope was reprocessed with this period in mind, something even stranger appeared. Spectral lines in the infrared, notably carbon dioxide and carbon monoxide emissions, fluctuated in phase with the brightness changes. Not only was the light blinking, the chemistry was too. Gas output rose and fell in sync with the photometric pulse. It was as if the comet was breathing. This revelation divided the community into 2 camps. One saw it as a natural harmonic oscillation, the result of internal thermal cycles, perhaps layers of volatile ices sublimating in waves through fissures that opened and closed as the nucleus flexed under heat. A self-regulating geyser, like a heartbeat in ice. The other camp found that explanation too clean. The timing was too stable, too mechanical. No natural system maintains that kind of precision while moving millions of kilometers through variable solar radiation. Something else was maintaining rhythm, but science thrives on restraint. No one dared to speculate publicly beyond physics. The official hypothesis became a compromise, periodic outgassing modulated by rotational subharmonics, a mathematical way of saying we don't really know, but it's probably normal. Still, the human mind doesn't easily accept coincidence stacked upon coincidence. Her comet with impossible symmetry, motionless under thrust, carrying isotopes from a vanished environment, and now pulsing like a clock. The narrative had grown too poetic to ignore. In private, scientists admitted what they would not write. Some felt uneasy. Others felt awe. A few simply stared at the plots in silence, as if waiting for the next pulse to mean something. The data was cold, but the experience was not. It was haunting. One night in December, a researcher at the Atacama Array took a long exposure image of Atlas's fading coma. The object was faint, little more than a smear, but when she enhanced the image, she noticed subtle concentric ripples, shells of dust expanding outward, evenly spaced like the rings of a tree trunk. Each shell corresponded to the 16-hour interval, a visible record of the heartbeat, a frozen echo of rhythm in space. The finding was quietly confirmed weeks later by another observatory using radar backscatter analysis. Tiny variations in dust density aligned perfectly with the photometric pulse. It wasn't illusion. Atlas truly pulsed, releasing faint shells of dust and gas in precise rhythm, like ripples spreading across water from an invisible stone dropped at regular intervals. The next question was inevitable. What drove it? The working model that emerged was elegant, if speculative. Deep beneath the surface, layers of frozen carbon dioxide and methane might form sealed pockets under thin crusts of dust. As sunlight penetrated, heat built up pressure until the crust ruptured, venting gas into space. Once the pressure released, the layer cooled, refroze, and the cycle began again. The period of cooling and reheating could, in theory, produce a rhythmic pulse, but the exact timing, so perfect, so unchanging, remained unaccounted for. Even simulations using known thermal properties of CO2 ices couldn't match the regularity. The thermal cycles drifted. Atlas didn't. By January, when the comet's brightness had dropped below visual thresholds, the heartbeat faded into the background noise, but its legacy persisted. Every paper that followed, every conference presentation, carried the same lingering tone, admiration mixed with unease. The rhythm might be natural. It might be coincidence, or it might be something we simply don't have the language to describe yet. A phenomenon sitting on the border between chemistry and choreography. In interviews, some astronomers described the feeling in philosophical terms. "We're used to randomness," one said, "but Atlas behaves like it's keeping time with something." Another put it differently. "It's not that it's alive, it's that it refuses to be entirely mechanical." In the public imagination, the comet's blink became a symbol. Memes, music, even poetry appeared online under the phrase, "the heartbeat of the void." To many, it felt like the universe itself had exhaled for a moment, revealing that even in emptiness, rhythm exists. Whether biological, geological, or cosmic, heartbeat means continuity. Atlas had become the first interstellar rhythm we'd ever recorded. And yet, as data analysts at NASA's Jet Propulsion Laboratory continued to refine the frequency, they noticed a detail that made them pause. The 16-hour cycle wasn't perfectly constant after all. It was drifting. Not randomly, but slightly lengthening over time, as though something were gradually slowing down. A deceleration too small to alter its orbit, too subtle to measure as force, yet undeniably real in the timing data. By the time optical telescopes could no longer see 3IATLAS, the story should have ended. Its light had faded beyond Hubble's reach. Its coma dissolved into invisible dust. Its heartbeat dimmed to silence. But sometimes endings leave traces, not in what we can see, but in what we can still hear. It started with data nobody was looking for. A radio astronomy array in South Africa, part of a program mapping the faint background hiss of the Milky Way, noticed something peculiar during calibration. Every 16 hours, the noise floor spiked ever so slightly. A subtle uptick in signal strength spread across multiple frequencies. The pattern was broad, diffuse, not like a transmission or burst. It was a whisper, a shimmer across the static. The technicians flagged it as a probable artifact of equipment synchronization and moved on. But one of them, a graduate student cross-checking timestamps, noticed the rhythm felt strangely familiar. 16 hours, the same period that haunted the light curves of Atlas months earlier. At first it seemed impossible. The comet was long gone, billions of kilometers away, now little more than a dark pebble drifting through the Kuiper region. Its light no longer reached us. Its heartbeat had faded into memory. Yet here, in the cold precision of radio data, the rhythm returned. Faint, persistent, mathematically exact. The team double-checked everything. They looked for instrumental drift, software oscillations, atmospheric refraction, even interference from orbiting satellites. Nothing matched the timing or periodicity. The signal wasn't local. It was cosmic. When they aligned the timestamps with the predicted position of 3IATLAS on its outbound trajectory, the coincidence deepened. Each radio pulse corresponded to the comet's geometric alignment with Earth, the times when our planet, the Sun, and Atlas formed near collinear positions. The pulses weren't random. They were synchronized with geometry. No one quite knew what to make of it. A decaying comet producing radio modulation from billions of kilometers away made no sense. The object was too cold, too inert, too small to generate emissions of that magnitude. But the data refused to vanish. The array in South Africa wasn't alone. Similar patterns appeared independently in observations from the low-frequency array in the Netherlands and faintly in the archives of the Allen Telescope Array in California. 3 instruments, 3 continents, 1 pulse. When the results were quietly shared in a private Slack channel among researchers, the conversation erupted. Some dismissed it outright. Coincidence stacked upon coincidence. Others felt a spark of cautious wonder. One astronomer wrote, "If it were any other frequency, I'd call it terrestrial. But this sits in the quiet band, the part of the spectrum where Earth is silent. That frequency band between 1 and 2 gigahertz is famously calm, used by cosmologists to listen for hydrogen line radiation and the cosmic microwave background. If you hear something there, it usually means the universe is whispering." Within weeks, a cross-continental collaboration formed to study the anomaly. They called it the Atlas Echo Project. Dozens of observatories pointed their dishes toward the empty patch of sky where the comet had last been seen. The first round of observations was inconclusive. The rhythm was weak, fading in and out, buried in galactic hiss. But when they stacked data from multiple nights and applied a Fourier transform, the pattern emerged clearly. A frequency modulation with a fundamental period of 16 hours, plus faint harmonics at 8 and 32. A harmonic ladder, the mathematical signature of a repeating process. The easy answer was reflection. Maybe solar wind particles were bouncing off lingering dust, creating periodic plasma oscillations. But the directionality was wrong. The pulses didn't follow the sun's activity cycles. They followed Atlas's trajectory, even weeks after its coma had dispersed. Something at that position, or perhaps something traveling with it, was interacting with the interstellar medium in rhythmic bursts. For scientists, that's both thrilling and terrifying, because the universe is full of radio noise, quasars, pulsars, solar flares, but they all have fingerprints. This one had none. It was too broad for a pulsar, too slow for magnetar rotation, too consistent to be noise. Whatever it was, it had never been catalogued before. The papers that followed were cautious to the point of monotone. They spoke of non-stationary broadband modulations possibly associated with residual plasma turbulence along the Atlas trajectory. But buried between the lines, the fascination was palpable. Everyone knew what the data implied, even if no one dared say it aloud. The heartbeat had left an echo. Theorists tried to model it. One suggestion was that the comet's passage had disturbed the interstellar magnetic field, leaving behind a filament, a twisting rope of charged particles oscillating as it relaxed back into equilibrium. If true, it would be the first time we directly detected the magnetic wake of an interstellar body. Another model proposed that the radio pulses were a byproduct of cosmic ray scattering. Tiny density waves rippling through the dust Atlas left behind, amplified by resonance effects. That could explain the persistence of the signal even after the comet's visible disappearance. But again, the timing remained the riddle. Why exactly 16 hours? Why so steady? To find out, researchers plotted the drift of the period over months. Just as the optical pulse had slowed slightly, the radio echo followed suit. Each subsequent pulse arrived a few seconds later than predicted, an elongation perfectly mirroring the decay rate of the optical rhythm. The two signals, separated by different wavelengths, different detectors, and different epochs, were synchronized across time. The heartbeat and the echo and light and radio were fading together, as though bound by a shared mechanism. This realization reignited public fascination. Media outlets resurrected the story, framing it as the comet that still speaks. Podcasts speculated about cosmic communication. Philosophers mused about rhythm as the universal constant. Meanwhile, the scientists wrestled with the sober difficulty of separating wonder from rigor. They knew that every discovery begins as coincidence and only later becomes law. But they also knew that some coincidences carry poetry too powerful to ignore. In late March, as the project compiled its final datasets, an unexpected contribution came from deep space telemetry engineers, the kind who monitor spacecraft far beyond Mars. They had access to low-frequency antennas designed to catch weak signals across billions of kilometers. Out of curiosity, one engineer pointed a receiver toward Atlas's outbound coordinates. The noise pattern came back faint, but the timing was unmistakable. The 16-hour pulse was still there, weaker but alive. When they combined that dataset with the global network's observations, a pattern emerged that no one had predicted. The pulses were not uniform in intensity. Every few cycles, a stronger burst appeared, modulated by a long, slow wave roughly every 22 days. That was too coincidental to ignore. 22 days is the approximate rotation period of the sun's magnetic field at its equator. Somehow Atlas's echo was resonating with the rhythm of our star. The idea spread quietly. Perhaps the object's ionized tail had entangled electromagnetically with solar plasma, forming a bridge, a resonant structure oscillating as both the sun and Atlas moved apart. a kind of interstellar harp string, plucked by solar wind and humming across space. It was beautiful. It was unprovable. And yet for many, it felt right. When the team published their final report, they titled it Persistent Electromagnetic Modulation Associated with 3IATLAS. The conclusions were humble. The source could not be confirmed. The mechanism remained uncertain. Further observations were encouraged, but in the final paragraph, hidden in cautious academic phrasing, one sentence stood out. The coherence between optical and radio periodicities suggests an underlying unity of process whose nature remains unknown. That line, understated, almost apologetic, and became legend. Because underlying unity of process is another way of saying, we don't understand why this thing behaves like it's alive. The echo eventually faded, swallowed by the rising noise of the galactic background. But before it disappeared, an observatory in Australia caught one final sequence. 3 pulses perfectly spaced, then silence. The data logs end there, a last heartbeat across the stars. To most scientists, that was the close of the file. To others, it was the beginning of something larger, an awareness that our instruments had brushed against a form of order we couldn't yet define. Whether it was physics, coincidence, or the echo of some cosmic memory, no one could say. But they all agreed on one thing. The experience had changed them, because once you've heard the universe whisper in rhythm, silence never sounds the same again. And yet, somewhere deeper in those archives, buried under lines of code and raw telemetry, analysts found something strange months later. A pattern within the pattern, a subtle frequency shift encoded in the last 3 pulses. Not random, not noise, a mathematical ratio repeated across wavelengths, one that corresponded improbably to the golden mean, and that discovery would reopen everything. The last transmission from 3IATLAS was supposed to be silence. 3 faint pulses, evenly spaced, then nothing. The final fading breath of a traveler vanishing into the cold. The world moved on. The data was archived, the instruments recalibrated, the night skies turned toward newer wonders. But in science, endings rarely stay still. Someone always looks closer. Months after the final echo, a data analyst at the Square Kilometre Array Processing Center reopened the files for calibration testing. It was routine work, comparing signal drift, cleaning residual noise. But while zooming into the final set of pulses, she noticed something off. Each of the 3 peaks wasn't identical. The timing between them was slightly irregular, off by fractions of a second. Differences too small to matter, yet too precise to ignore. Out of curiosity, she divided the intervals. The ratio was 1.618, the golden ratio. At first, she laughed. Coincidences like that litter big data sets. Randomness, given enough room, imitates perfection. Still, the pattern tugged at her mind. The golden ratio, F, isn't just a number. It's the geometry of growth, the rhythm of spirals in seashells and galaxies alike. It's the fingerprint of balance that nature seems to favor, even without reason. Finding it in 3 fading pulses of radio noise was absurd, and yet somehow fitting. She sent a quiet message to her supervisor, attaching the graph and asking if the ratio was real or a rounding artifact. Within hours, Half a dozen analysts were looking at the same file. They recalculated from raw data, removed compression filters, even corrected for the Doppler drift caused by Earth's rotation. The ratio held. It wasn't rounding. It was there, embedded in the timing itself. 3 pulses. Intervals in golden proportion. Word spread quickly, first through encrypted group chats, then through official channels. It wasn't an announcement, more like a rumor that refused to die. The astrophysical community had seen countless coincidences before, repeating numbers, symmetrical alignments, false patterns born of human bias. But this one was different. Because F, the golden ratio, is not arbitrary, it's fundamental. It governs the stable configurations of dynamical systems, from the orbits of moons to the spacing of petals, from the architecture of hurricanes to the shape of DNA. It is the mathematics of equilibrium, order emerging from chaos. And here it was, whispering from a dying comet that shouldn't have had anything left to whisper. Skeptics moved fast. They argued it was statistical noise. When you analyze enough data, you'll always find patterns that mimic meaningful constants. Others pointed out that 3 points can produce any ratio you wish if the scale is small enough. But the deeper they looked, the less random it seemed. Not just the intervals, the frequencies themselves exhibited harmonic spacing related by EF. The ratio repeated across wavelengths, as if encoded in the very structure of the signal. When plotted on a spectrogram, the pattern resembled a spiral, faint, elegant, self-similar across scales. Not an image, not a code, just mathematics woven through noise. The official line was cautious, likely an artifact of non-linear interference. But privately, the scientists weren't so sure. They'd seen interference before, chaotic, irregular, messy. This wasn't that. This was symmetry, and symmetry in physics is never meaningless. At a small symposium in Geneva, the data was presented quietly under a different name, phi-resonant spacing in broadband decay. No one used the word golden. The atmosphere was sober, almost reverent. Slide by slide, the researchers showed the numbers, the spacing, the harmonic ladder, the logarithmic slope. Each measurement aligned with F to the 3rd decimal. Too clean, too human, too beautiful. Someone in the audience finally said what everyone was thinking. If this were art, we'd call it design. The room fell silent. The lead presenter, a radio physicist with 20 years of experience, responded quietly, "Yes, but beauty isn't proof. It's only invitation." And that became the guiding philosophy of what followed, the phi hypothesis, as journalists later called it. The idea wasn't that Atlas was sending a message. It was that something about its structure, its geometry, its internal dynamics, resonated with the same principles that govern natural harmony across the universe. Perhaps its rotation, sublimation cycles, or magnetic interactions had fallen into a self-organizing pattern that happened, by physics alone, to mirror F. A cosmic coincidence, yet a meaningful one. Because coincidences, when repeated across scales, become law. Theorists from plasma physics to chaos theory began to weigh in. Some saw it as evidence of spontaneous symmetry restoration, the tendency of complex systems under decay to settle into golden ratios as they dissipate energy efficiently. In other words, F is the most stable path towards silence. A comet dying into equilibrium, choosing harmony as its last act. Others dismissed the poetry and focused on mechanics. Resonance frequencies between rotational harmonics and sublimation pulses could mathematically yield F under specific parameters. It didn't need mystery, just math. But even the math was haunting. Because if correct, it meant Atlas had found the most efficient way to fade, a perfect cosmic death spiral, elegant and inevitable. Meanwhile, the public latched onto the symbol. Documentaries called it the comet that died beautifully. Artists painted golden spirals against black space. Spiritual commentators declared it proof that the universe was conscious, that geometry itself was divine language. Scientists grimaced at the sensationalism, yet privately many couldn't shake the awe, because beauty, even when misinterpreted, still moves the soul. Back in the labs, efforts turned toward replication. Could this pattern be simulated? Teams built models of cometary outgassing, particle dispersion, and plasma echoes in magnetized space. They input random noise, variable cycles, thermal decay, but none produced F with the precision observed. Every model came close, never perfect. Reality, it seemed, had been closer to ideal than theory could reproduce. That paradox bothered them. How could a natural object, born in chaos and decay, produce the same mathematical perfection humans use to define beauty? Was it truly coincidence? Or was beauty itself the fingerprint of universal efficiency? Late one night, one of the researchers wrote in her lab notes, "Maybe the universe doesn't imitate design. Maybe design imitates the universe. It was never meant for publication, but someone leaked it." Within days, it was quoted across headlines, fueling another storm of speculation that scientists had found God in a comet. They hadn't. What they'd found was deeper and quieter, a pattern that suggested harmony as a property of entropy itself. The more they studied, the more the implications deepened. When they overlaid the F-based decay of the ATLAS signal with known astrophysical phenomena, orbital resonances of Jupiter's moons, the spiral arms of galaxies, the oscillation ratios of certain variable stars, they found echoes everywhere. Not identical, but parallel. The same number appearing in systems as small as atoms and as vast as galaxies. A universal rhythm hiding in plain sight. It was then that a philosopher of science, invited almost as an afterthought to one of the conferences, summarized what everyone else had been trying to say. Perhaps Atlas isn't special because it showed us something new. Perhaps it's special because it reminded us of something we forgot, that order doesn't need intention to exist. The room fell quiet. For once, there was no debate, just agreement, heavy and fragile. In the months that followed, the data was peer-reviewed, reproduced, and slowly accepted as authentic, but interpreted modestly. A natural resonance, nothing more. Yet beneath the modesty, reverence lingered. Because science, when honest, admits wonder. Years later, when the golden ratio finding was revisited in documentaries, most physicists framed it pragmatically. They explained it as the geometry of efficient decay, the mathematics of equilibrium. But when asked privately what they felt, their answers were different. They spoke not of equations, but of something human, that fleeting awareness that the universe speaks in patterns too elegant to dismiss as chance. Atlas had not shouted across space. It had whispered through proportion. It had not signaled intelligence, but it had displayed intelligence's favorite language. In its dying rhythm, it mirrored the same balance that shapes galaxies, flowers, seashells, and perhaps minds. And so the comet's legacy changed shape once again. It was no longer just the traveler from another star, or the object that blinked, or the source of an echo. It became something gentler, the reminder that even in randomness the universe chooses grace, that even decay can compose music. But the story didn't rest there, because as simulations continued, a new anomaly emerged, one hidden not in timing or frequency, but in trajectory itself. A minute, inexplicable drift detected in the comet's outbound path, as though in its final departure it had subtly turned towards something unseen, and that is where the next chapter begins. Space is supposed to be predictable. That's its comfort and its cruelty. A place where everything obeys gravity's arithmetic, where motion can be plotted, predicted, and proven centuries ahead. But sometimes something shifts, and that shift, no matter how small, shakes the faith that the universe is entirely knowable. For 3IATLAS, that moment came quietly, long after its light had vanished. By the time most telescopes had stopped tracking the comet, it was deep in the outbound corridor, more than 6 astronomical units away, farther than Jupiter, dimmer than memory. But a few deep space stations still pinged its coordinates from habit, running automatic ephemeris updates for completeness. They expected a perfect match between prediction and reality. Instead, they found a whisper of rebellion. At first it was nothing, a positional discrepancy of just a few arcseconds, less than the width of a human hair seen from a kilometer away. No one noticed. But when the data accumulated over weeks, the offset grew. Not by much, but enough. By the end of the quarter, the deviation exceeded all modeled uncertainties. Atlas was off course. The standard explanations came fast. Instrumental drift, parallax miscalculation, light pressure, thermal recoil. But every correction left the residual untouched. It wasn't error. It was motion, an acceleration so gentle it could barely be measured, yet persistent, steady and directed. It wasn't pushing the comet away from the sun, as solar radiation would. It wasn't being tugged by Jupiter or Neptune or any known mass. It was curving slightly, deliberately, toward the galactic north. When the anomaly was first published in an internal report, it drew little attention. Tiny trajectory deviations are common among comets, caused by asymmetric outgassing or structural rotation. But those effects vanish once the object becomes inert. Atlas had long since gone silent. No jets, no heat, no spin variation. And still it moved. To an outsider, the numbers looked trivial. A few millimeters per second squared, an infinitesimal nudge. But in space, even whispers accumulate. Over months, that drift translated into thousands of kilometers of deviation. Not random, not chaotic, but smooth, as if following a new invisible current. Astronomers ran models for every plausible cause. They tested gravitational perturbations from passing stars, micrometeoroid impacts, solar wind pressure, even dark matter density gradients. Nothing fit. The vector was wrong. Slightly tilted, slightly purposeful. Almost like the comet had caught a tailwind that no one else could feel. Then came the strangest observation. When the direction of the drift was plotted against the galactic map, the line extended almost precisely toward a point known as the local velocity convergence, a region of space where the motions of nearby stars seem to align, a quiet river in the galactic sea. To most, it was coincidence. To a few, it felt poetic, as though the interstellar traveler, after visiting us, had simply turned homeward, following a current older than light. Still, scientists don't believe in poetry, not officially. They wanted data, so they dug deeper, tracking every known factor that could possibly explain the motion. Solar wind? Too weak at that distance. Yarkovsky effect? Impossible without rotation. Mass loss? No measurable coma, no dust plume, no tail. It was as if something internal, something invisible, was still exerting force. Some suggested sublimation of hypervolatile ices like molecular nitrogen or carbon monoxide trapped deep within. Even a trace amount could create microthrust if vented asymmetrically. But that would have produced flickers in brightness, and none were seen. Others floated exotic physics, interactions with interstellar magnetic fields, pressure from dark photons, even quantum-level anisotropies. Every theory stretched, none held. The anomaly became a ghost topic, whispered about, rarely published. To admit it was to risk ridicule, the fate of those who chase phantoms in data, but the numbers persisted, quietly updated in ephemerides with each new observation, each time refusing to vanish. Whatever was moving Atlas, it hadn't stopped. In March, the European Space Operations Center published a terse internal note. Observed non-gravitational acceleration consistent across 5 independent datasets. Magnitude 3.8 8 ms2. Direction galactic northward stable. No explanation. Just acknowledgement. That acknowledgement changed everything, because this wasn't the first time. Oumuamua, the first interstellar visitor, had shown a similar unexplained push as it left the solar system. Its acceleration had been stronger, but the pattern was hauntingly familiar. Both objects, unrelated in time or origin, had entered from the deep and exited under invisible influence. 2 data points don't make a theory, but they make a question, and questions spread faster than comets. Soon, old debates resurfaced. Radiation pressure, exotic propulsion, unknown materials. Theorists proposed that both Oumuamua and Atlas might share a physical property unseen in solar system bodies. Ultra-low density fractal surfaces capable of interacting with solar photons like sails. That would explain their trajectories, light itself pushing them onward. But calculations showed that Atlas was too massive, its albedo too low. It couldn't sail on light, and yet it drifted. Privately, some began to suspect the anomaly wasn't mechanical at all, but gravitational. Perhaps the standard solar potential was subtly wrong. Perhaps we were missing a layer of curvature in space-time, a gentle gradient too small to affect planets, but enough to guide fragile travelers. A hidden current in the cosmic fabric. If true, it would mean every interstellar body passing through would follow the same unseen path. A pattern written not in matter, but in geometry. A few dared to call it what it felt like, a trail. As if interstellar space itself had memory, gently pulling its exiles along routes carved by countless predecessors. A galactic migration lane, invisible yet real. Of course, the official community kept its distance from such metaphors. The phrase persistent systematic residual became the safe term. But among those who had spent their careers studying celestial mechanics, the unease grew. Because the equations weren't supposed to care about poetry, yet the universe kept writing it anyway. By the summer, the anomaly was undeniable. Atlas's position, verified by radar ranging from the Deep Space Network, showed an offset of 11,200 kilometers from its predicted path. Minuscule in cosmic scale but immense in precision, it meant that somewhere in the cold between stars, a constant, quiet force was still at work. Then came the final twist. When the direction of the drift was compared to the vector of Atlas's initial inbound trajectory, something astonishing appeared. They weren't random. They were parallel and almost perfectly. The comet had arrived along one line and was leaving along another, both pointing within a fraction of a degree of the same galactic coordinate. No gravitational scattering, no deflection, as if it had entered and exited along the same invisible rail. To a mathematician, that was elegance. To a physicist, impossibility. Nothing that passes through a gravitational field leaves unchanged, not unless the force pulling it also lets it go in perfect symmetry. One astrophysicist at Caltech described it as cosmic courtesy, the universe holding a door open both ways. It sounded absurd, but the math didn't argue. Whatever path Atlas followed, it obeyed geometry we hadn't yet written down. When the final orbital report was published, it concluded with the driest line imaginable. Residual acceleration remains unaccounted for. Further investigation recommended. That sentence, stripped of wonder, marked the border between knowledge and humility. Outside the journals, the story took a life of its own. Articles called Atlas the comet that refused gravity. Philosophers called it the wanderer that remembered home. But in scientific circles, something subtler changed. A quiet shift in tone, an unspoken recognition that the tidy certainty of celestial mechanics had been fractured, that even in a universe ruled by equations, something mysterious still moves unseen. For months afterward, the Anomaly haunted simulation labs. Researchers tried to replicate the drift with virtual comets. Every time their models either spun apart or settled into stillness, none could reproduce motion that felt deliberate yet natural. Eventually, one exhausted modeler wrote in her notes, "It moves as if following an instruction we don't yet know how to write." The phrase stuck, because perhaps that's what 3IATLAS truly was, a traveler following a law too subtle for our eyes, too elegant for our instruments, not breaking physics, but revealing how incomplete our version of it still is. Maybe the universe has more verbs than we've learned to speak, and so the comet receded, fading into the star fields beyond Neptune, still curving gently toward the galactic north. Its silence grew deeper, its position fainter, its mystery brighter. All we could do was watch, and imagine that somewhere, beyond the thin reach of our equations, a hidden current carried it onward, toward destinations we can't yet chart. Because maybe, just maybe, motion itself remembers, and as the last data packet closed, one final question lingered in every astronomer's mind. If every force leaves a trace, what force leaves beauty? When the drift of 3IATLAS could no longer be ignored, astronomy found itself at an uncomfortable crossroads. For centuries, motion had been the one thing we could trust. Light deceives, color lies, but movement obeys. Every planet, every comet, every photon follows the curve of space with obedient precision. And yet, here was a traveler that seemed to obey a deeper rule, one we hadn't yet written. In the aftermath of the Anomaly reports, the community fractured into quiet camps. One insisted that the data was incomplete, that somewhere hidden in the coma or composition was a small but explainable thrust. The other camp, smaller but louder, suspected something stranger, that 3IATLAS had revealed not an exception but a structure, a pattern too large to notice until something passed through it. They called it, almost poetically, the hidden current. The name came from an analogy. When ships first sailed across the oceans of Earth, they discovered invisible paths where the sea itself moved. The Gulf Stream, the Kuroshio, the Agulhas. You could not see them, but if you entered one, the world seemed to glide beneath you. Perhaps the theorists suggested the galaxy was the same. Perhaps there are rivers in space-time, faint gradients of curvature or energy density, that objects can drift along effortlessly once they cross into them. Not magic, not propulsion, guidance. It sounded romantic, but the math began to whisper in agreement. General relativity, for all its perfection, describes gravity as geometry. Space bends, time stretches, and matter follows the easiest route through that landscape, the geodesic. But the galaxy is not static. Its mass distribution changes constantly as stars orbit. Gas flows and dark matter hums unseen. In that churning, the geometry of space itself may create subtle pathways, dynamic geodesics that move like streams in a cosmic ocean. They are not forces but tendencies, directions that require less energy to follow. In theory, such currents would be invisible, detectable only when something lightweight and free, like 3IATLAS, drifts through them. Planets bound to their stars would never notice. Spacecraft propelled by thrust would override them. But an interstellar wanderer, cold and untethered, could slip into one and ride it silently across light years. It was an extraordinary claim. But extraordinary claims are built from patient mathematics, not metaphors. So the work began. At the Max Planck Institute, a team constructed high-resolution galactic potential models, incorporating not just baryonic matter, the stars and gas we see, but dark matter density waves derived from cosmological simulations. When they mapped the resulting curvature field, they found something astonishing: faint, filament-like channels threading through the Milky Way's disk, regions where gravitational gradients flattened into smooth corridors extending hundreds of light years. Objects entering such regions would experience minute accelerations, nudged gently along their length, the exact magnitude seen in Atlas. The currents were theoretical, but their predicted geometry matched the comet's path almost perfectly. By coincidence, or confirmation, Atlas's outbound drift aligned with one such filament, a region extending from the solar neighborhood toward the galactic north, precisely where its anomaly pointed. Suddenly, the impossible felt logical. Still, skepticism ran deep. Dark matter, though accepted, was already a mystery. Now it was being asked to dance. Many argued that the alignment was mere coincidence, a map drawn to fit a conclusion. But even skeptics couldn't deny that the numbers were seductive. If real, these hidden currents could explain not just Atlas, but Oumuamua, and perhaps countless unseen travelers that had passed unnoticed for eons. To test the theory, astrophysicists turned to simulations. They seeded millions of particles into virtual galaxies, each free of propulsion, and watched them drift over billions of years. To their surprise, the particles didn't spread evenly. They clustered into long thread-like streams, flowing along invisible rails formed by the collective motion of stars and dark matter. When color-coded by velocity, the result looked eerily like a fluid map, rivers of space gliding through the galactic sea. The visual stunned even the modelers. It was beautiful, but more than that, it was predictive. The simulated currents passed directly through the region of space our solar system currently occupies, a quiet spiral branch of the Orion Arm. And the flow within that branch pointed almost exactly toward the same direction as Atlas's. Drift, the theory solidified. Our solar system might lie near a gravitational eddy, a slow, stable swirl in the galactic flow, and Atlas, upon passing through, simply followed the current onward. Not propulsion, not mystery, just the quiet pull of geometry, unnoticed until now. In private conferences, scientists called it the most humbling revelation since Einstein. If true, it meant that space itself wasn't static emptiness, but dynamic texture, a living fabric with tides and eddies, shaped by the invisible hand of mass. Every interstellar object, every wisp of dust, every lost spacecraft might one day find itself swept gently into these flows, carried far beyond its intended course. But as always, truth breeds questions faster than answers. If the galaxy has currents, can they be mapped? Can we navigate them? Could a civilization, if it existed, use them as highways, crossing the stars without fuel, without thrust, just patience and knowledge of the flow? The thought was intoxicating, yet no one dared publish it aloud. Instead, the idea hid in footnotes, dressed in cautious language like energy-minimizing trajectories and dynamic equilibrium pathways. But to those who dreamed quietly, Atlas had done more than drift. It had traced a path humanity might someday follow. As the models grew more sophisticated, new curiosities appeared. Some filaments converged, points where multiple currents met before diverging again, like confluences of rivers. Theorists called them gravitational estuaries. These nodes, they realized, could act as gathering points, regions where interstellar material naturally accumulates over millennia. Perhaps even where objects from many origins meet. No one said the word, but it lingered. Hubs. The deeper they looked, the more poetic the picture became. Our galaxy wasn't a void. It was an ocean. Its stars were islands, and between them flowed unseen tides, slow and patient, shaping the destinies of wanderers we hadn't even known existed. Atlas, then, was not a messenger. It was a driftwood branch revealing the current beneath the surface. Still, proof remained elusive. Detecting such currents directly would require instruments beyond our reach, sensors capable of measuring space-time curvature variations smaller than a billionth of gravity. We could only infer their existence by the paths of things that floated within them, and so telescopes turned outward again, watching for the next interstellar visitor. Because if the next traveler curved in the same direction, if it too drifted toward galactic north, the case would strengthen beyond coincidence. Until then, the hidden current remained theory, fragile, beautiful, and unprovable. Yet even as scientists argued over equations, a quieter revelation took root. The idea that space was alive in motion, that the universe wasn't static but breathing, stirred something old in the human imagination. It echoed ancient myths of celestial rivers and silver pathways across the night sky. What we had dismissed as poetry, perhaps, had always been physics. In a lecture months later, one of the lead theorists spoke to a room of students and journalists. He described the equations, the potential wells, the curvature maps, all precise, all rigorous. Then he paused, looked up, and said softly, "If the galaxy truly has currents, then motion itself is a conversation between matter and memory." The room went still. Every traveler that passes through leaves a trace of where it has been, and in doing so, slightly alters the flow for those who follow. Perhaps that's why Atlas moved the way it did, not because it was pushed, but because it was remembered. It was a poetic statement, but it captured the essence of the moment. Because maybe that's what science really is, the act of remembering the universe through patterns we can measure. When the lecture ended, a student asked the question everyone secretly carried. If these currents exist, where do they lead? The physicist smiled faintly and replied, "Everywhere worth going. We just don't know the routes yet." That night, telescopes in Chile and Hawaii turned back toward the region of sky where Atlas had last been seen. There was nothing, no echo, no light, no trace. And yet when the data came back, one observer noticed a faint streak near the limit of detection. Not bright enough to identify, not strong enough to track. But it was moving along the same line, quietly, steadily toward the galactic north. Maybe coincidence, maybe confirmation. Either way, the river was still flowing. Months passed after 3IATLAS vanished into the galactic north, and the world slowly forgot. The data was filed, the equations archived, the fascination left to documentaries and quiet late-night conversations among astronomers who still whispered about the current. But the sky has a way of remembering what we forget. Because one winter morning before sunrise, the first alert came through the minor planet center. New fast-moving object detected, hyperbolic trajectory. At first, no one paid it much attention. The observatory in Arizona that found it reported it as a typical transient. Faint, fast, ordinary. The data came in raw, incomplete, wrapped in the usual margin of uncertainty. But when its path was calculated, something uncanny appeared. Its inbound vector, the direction from which it came, pointed within 2 degrees of the same galactic coordinate from which 3IATLAS had arrived, and its velocity, almost identical, 58.4 kilometers per second. The astronomer who noticed it reportedly froze at his desk, staring at the numbers as if they'd repeated themselves. The next night, follow-up observations confirmed the hyperbolic trajectory. This was no bound object. It was another visitor, another interstellar traveler, and it was coming along the same invisible highway. The media hadn't yet caught wind, so for the first few days the discovery remained within the community. Emails and encrypted chat channels lit up with a single question whispered again and again. Is it following the current? By the third week, confirmation arrived. The object, temporarily designated 3I Viriditas, was approaching from nearly the same radiant as Atlas, with a trajectory only slightly offset but parallel, as if tracing the path of its predecessor with patient precision. The odds of two unrelated interstellar comets entering from almost the same direction with nearly identical speeds were infinitesimal. Something was happening. Either coincidence had become conspiracy, or the hidden current was real. As data poured in, astronomers noticed other similarities. Viriditas was faintly green, its coma tinted with the spectral lines of cyanogen and diatomic carbon, the same molecular fingerprints as Atlas. Its light curve was stable, its rotation slow, its polarization curve eerily similar. Even its faint gas jets, when modeled, seemed to align in the same pattern, spiraling outward as if shaped by the same invisible hand. The resemblance was unsettling. It was as though the galaxy had sent another messenger, carved from the same memory, sailing along the same silent river of space. The first press release came cautiously, phrased with academic restraint. A new interstellar comet, 3I Viriditas, has been detected. Preliminary analysis suggests similarities to 3IATLAS in both trajectory and composition. But behind the neutral words, the sense of wonder and unease was palpable. It was the first time in recorded history that two interstellar visitors had followed nearly identical paths. Even the skeptics, those who had dismissed the hidden current as poetic nonsense, fell silent. Because if coincidence happens twice, it begins to look like pattern. When the first high-resolution spectrum arrived from the Keck Observatory, the shock deepened. Viriditas shared Atlas's impossible chemistry, the same anomalous deuterium enrichment, the same solar normal nitrogen ratio, the signature of an environment that doesn't exist anymore. It was as if both comets had been born from the same ancient nebula, long vanished into galactic dust. Two fragments from the same lost world, separated by light years and time, now arriving in sequence, like echoes of each other. For months, the research community lived in a state of quiet obsession. Meetings stretched into dawn. Simulations ran endlessly. Papers appeared, then vanished again under peer review. Everyone knew what was at stake. If the trajectories truly matched, the implication was enormous. The galaxy had structure, real gravitational structure, that shaped interstellar travel. The hidden current was no longer theory, it was map. In the quiet corridors of observatories, scientists whispered about something else too, something they didn't want on record. Because Viriditas wasn't just following Atlas's path through the galaxy, it was following its story. 2 weeks into observation, a modulation appeared in the light curve. Faint, rhythmic, impossible to miss. 16 hours at first, no one said it aloud. The number hung in the data like a ghost waiting to be acknowledged. It couldn't be. It shouldn't be. But there it was, the same heartbeat. This time they moved faster. Multiple observatories confirmed the periodicity. Unlike Atlas, whose heartbeat had been a fading whisper, Viriditas pulsed clearly, steadily, almost proudly. The amplitude was stronger, the timing more stable, the signal unmistakable. It was as though the same rhythm that had haunted one comet had found its voice in another. The reactions divided the world. To some it was cosmic repetition, natural processes mirroring each other through the same physics. To others, it was pattern beyond coincidence, A message written in rhythm, broadcast not in words but in recurrence. The same current, the same chemistry, the same pulse. It was as if the universe was repeating itself, rehearsing a theme in variations. As the data poured in, theories multiplied. Perhaps the 16-hour pulse was a natural oscillation of sublimation under similar thermal conditions. Perhaps the hidden current wasn't just guiding movement but synchronizing rotation. Cosmic metronomes ticking in phase along the same gravitational flow. In fluid dynamics, waves in connected channels can synchronize spontaneously. Maybe the galaxy's fabric behaved the same way. Maybe Atlas and Viriditas were simply instruments resonating with the same background music of the cosmos. But deep down, everyone felt the strangeness. Two bodies from unknown origins, separated by time and distance, entering our system along the same path, spinning to the same rhythm, whispering in the same light. Coincidence was running out of breath. For weeks the pulse dominated headlines. News anchors called it the heartbeat of the galaxy. Podcasts speculated about signals, about consciousness, about the possibility that these comets were not wanderers but messengers. The scientific community tried to stay composed, issuing careful statements about physical explanations. Thermal tides, spin harmonics, sublimation cycles. But privately, even they began to speak of pattern as destiny. Then came the discovery that turned speculation into revelation. When the European Space Agency's Gaia mission recalculated the trajectory of Viriditas backward through space, tracing its probable origin, the path intersected with the outbound line of 3IATLAS, not in our solar system but beyond it, far beyond. At a point nearly 12 light-years away, in interstellar space, the two paths crossed as if they had once passed through the same invisible gate. That convergence point lay near a faint red dwarf star catalogued long ago but seldom studied. Luyten 7268, an unremarkable binary system, ancient, stable, surrounded by faint dust streams. But now all eyes turned toward it, because if both comets had emerged from that region, then perhaps that was where the hidden current began, or where it ended. Proposals flooded funding agencies overnight. Missions, probes, simulations. Everyone wanted to trace the current, to understand the mechanism that could send two bodies across light years on parallel paths. Some dreamed of riding it, building future spacecraft that could drift along the galaxy's gravitational rivers, crossing the stars not by brute force, but by surrender. It was the oldest dream in science, to turn knowledge into navigation. And then, just as it had with Atlas, the unexpected happened again. As Viriditas neared perihelion, brightening in the sunlight, its rhythm faltered. The 16-hour pulse began to slow. 16 hours and 2 minutes, then 16 hours and 10. And within that slowdown, another pattern emerged, a faint modulation, a secondary pulse repeating every 22 days. The same period as the solar magnetic rotation, the same harmonic found in Atlas's radio echo. It was happening again. The symmetry, the timing, the resonance, all of it. When scientists overlaid the two datasets separated by years, they aligned perfectly. Different objects, same tempo, same drift, same whisper. It was as if the galaxy itself was speaking in repetition, and 3IATLAS had merely been the first syllable. Late one night, a researcher staring at the combined light curve noticed something else. The shape of the amplitude modulation, the precise rise and fall of the brightness. When he normalized the scale and plotted it logarithmically, it matched the same golden ratio curve derived from Atlas's final radio echo. The same spiral, the same geometry, repeating again in another traveler. And then, for the first time, fear entered the conversation. Because if one coincidence can be ignored, and two can be debated, three begin to demand belief. It meant there was structure. Something in the galaxy, gravitational, magnetic, or otherwise, was organizing matter into rhythm and proportion. And if that structure existed, it didn't just shape comets, it shaped everything. By the time Viriditas began its outbound path, the silence in the astronomy community was deafening. Everyone was watching, waiting, terrified of what they might see next. Would it drift north like Atlas? Would it curve along the same hidden current? Would it too vanish in symmetry? Weeks later, the final radar observations came in. Viriditas had crossed the orbit of Mars, its faint coma thinning, its light dimming, and its trajectory had begun to curve. Exactly as predicted, the same vector, the same destination, the same quiet, deliberate departure into the galactic north. It was official. The current was real. When 4I Viriditas curved into the same northward drift traced by 3IATLAS, astronomy changed forever. It was no longer speculation, no longer metaphor. Two bodies from two epochs, both moving in synchrony along an invisible road. The phrase hidden current vanished from quotation marks. It became theory, then fact. And with fact came the oldest instinct of all, to map it. In the months following Viriditas' departure, observatories across the planet entered a kind of fevered collaboration. Supercomputers once reserved for simulating galaxies were redirected to charting the finer geometry of space itself. Astrometric data from Gaia, gravitational microlensing surveys, radio pulsar timing, even the faint distortions in the cosmic microwave background, all were layered together, pixel by pixel, to reveal the subtle texture of our galactic neighborhood. If gravity could flow like a tide, they wanted to see its surface. At first, the results were chaotic, noise, overlapping vectors, contradictions. But then patterns began to emerge, streams of motion invisible to the eye, revealed only in the statistics of billions of stars. Tiny biases in their velocities formed filaments, faint linear threads winding through the galactic disk. Each one was a corridor where gravitational potential flattened into smoothness, creating channels of near frictionless drift. Like veins in stone, like arteries in light, the simulations called them geodesic filaments. But within weeks the public had given them another name, the map of currents. It was unlike anything astronomy had ever produced, not an image of stars, but of the spaces between them. A living tapestry of motion, invisible until something happened to pass through it. And when the orbits of 3IATLAS and 4I Viriditas were overlaid on that tapestry, the alignment was perfect. Both traced the same thread, a narrow gravitational corridor running outward from the Sun toward the galactic north, bending slightly along the Orion arm before dissolving into the halo beyond. It was a cosmic artery, and we were standing on its bank. For the first time, humanity saw evidence that space was not empty chaos, but structured harmony. Gravity, once thought to be the simplest of forces, revealed a complexity more fluid than field, a choreography sculpted by time itself. To those who had spent their lives mapping galaxies, the revelation felt almost biological. Because the filaments didn't just flow, they branched. Each current divided into tributaries, merged again, then separated, like capillaries feeding a living system. Some formed closed loops, others stretched endlessly into the dark. The galaxy, it seemed, was not a static disk but a pulsing organism of motion, its matter circulating through invisible arteries of curvature. The analogy wasn't poetic exaggeration. It was mathematical truth. When the equations were simplified, the structure of the currents resembled fluid turbulence at the edge of order, neither random nor regular, but self-similar across scales. The same geometry appeared in neural networks, river deltas, even the vascular systems of leaves. It was as if the same law shaped everything that moves, from blood to starlight. Some physicists resisted the metaphor, but others embraced it. One lecture at Princeton opened with a provocative slide, a cross-section of a human lung beside the new gravitational current map. The caption read simply, "Two systems optimized for breath," because, in a way, the galaxy was breathing, inhaling and exhaling through its stellar arms, distributing motion the way lungs distribute air. And in that rhythm, Atlas and Viriditas were no longer anomalies. They were red blood cells of the cosmos, swept along the galactic flow. But mapping was only the beginning. The real question was, could these currents explain everything else? The long-standing mysteries of galactic dynamics, warps in the disk, spiral arm persistence, even the strange alignment of interstellar magnetic fields, all began to fall into place when viewed through the lens of flow. The currents didn't just move matter, they shaped it. Where they converged, stars formed. Where they diverged, emptiness grew. And where they pulsed, where periodic compression occurred, the galaxy sang in radio frequencies that matched, impossibly, the same harmonics measured in Atlas's fading echo. A physicist from Kyoto described it best in a single line. The galaxy is not an object. It is an act of motion so large and slow we mistook it for stillness. The discovery rippled through every field. Astrophysics, cosmology, even philosophy found itself rewritten. The hidden current had become a unifying principle, linking chaos theory to celestial mechanics, biology to thermodynamics. What had once been metaphor, the universe as living system, was now hypothesis, perhaps even fact. And yet, amid the triumph, unease lingered. Because buried within the new maps was something no one expected. In the region north of the Sun's path, where Atlas and Viriditas had vanished, the currents converged into an extraordinary structure, a vortex, a region of space where multiple filaments twisted together before vanishing into a zone of turbulence. It wasn't a black hole, nor a star cluster, nor any known gravitational anomaly. It was simply motion, a whirlpool of trajectories, the largest coherent flow yet discovered, and everything that entered it seemed to disappear. In models, the vortex looked like a spiral storm, elegant, stable, ancient. Some called it the Gaia. Its size was staggering, hundreds of light-years wide, centered in a quiet region of the galactic halo. Its gravitational field was perfectly balanced, not attracting, not repelling, just turning. A place where movement folded back upon itself. When the trajectories of other interstellar objects were retroactively modeled, many showed faint signatures of the same destination. It was as if the Gaia was the heart of the current system, the point toward which all motion gently converged, a gravitational estuary into which the rivers of space drained. The implications were staggering. If real, the Gaia could act as a natural trap for interstellar debris, comets, asteroids, even light. A vast, slow whirlpool collecting the galaxy's forgotten fragments. But deeper analysis revealed something stranger. The center of the Gaia was not empty. Within its core, gravitational simulations predicted a stable zone, a pocket of equilibrium where space-time curvature flattened entirely, a void inside the vortex, a still point within motion. One scientist, upon seeing the simulation, murmured almost involuntarily, "The eye of the galaxy." The phrase stuck. What existed in that eye, no one knew. It wasn't mass, it wasn't energy. It was geometry itself standing perfectly still, a balance point where the equations of motion collapsed into symmetry. Some suggested it might be a remnant of early galactic formation, a fossil whirlpool left from the Milky Way's birth. Others speculated it was something far older, a region where the universe's initial conditions had never fully unraveled. A preserved pocket of the primordial field, whatever it was, that's where Atlas and Viriditas were heading. Their paths extended forward through time, curved gracefully into the Gaia's outer arms. Within a few thousand years, they would reach its edge and join the countless invisible travelers already circling its heart. Two tiny fragments returning, perhaps, to the place where all motion began. The thought unsettled some, inspired others. It suggested that interstellar movement might not be random at all, that the galaxy recycles its wanderers, pulling them home through unseen currents, dissolving them into the great rotation of time. A cosmic circulation of memory. If true, it meant every interstellar comet we've ever seen, Oumuamua, Borisov, Atlas, Viriditas, was part of an ancient choreography. Not messages, not miracles, but participants in the same vast cycle, tracing the veins of the Milky Way like blood returning to a cosmic heart. It was the kind of realization that blurs the line between science and awe. Because in that map, that delicate glowing web of currents and vortices, humanity saw its first true glimpse of the living structure of space. Not alive in the biological sense, but alive in continuity, in rhythm, in purpose. A universe that doesn't just exist, it behaves. As the first complete map of galactic currents was released to the public, the image went viral overnight. A golden spiral of light veins threading through a sea of darkness, converging toward the halo's invisible eye. Artists called it the breath of the galaxy. Poets called it the skeleton of time. Scientists, still cautious, called it a model under review. But everyone, everywhere, felt the same tremor of recognition. Because the pattern looked familiar. It looked like us. The filaments mirrored the networks of our neurons, the branching of our veins, as above, so within. In a quiet press conference, one of the lead astronomers addressed that very point. Standing before a projection of the map, she said, "We used to think the universe was indifferent. But maybe it's participatory. Maybe every particle, every planet, every life form is a cell in a larger body, one that learns, remembers, and flows." The audience was silent for a full minute before the applause began. It was the kind of statement that belongs to history, not for its certainty, but for its courage. Because for the first time, science had drawn something that felt like a mirror. And yet, even as humanity celebrated its new understanding of the galactic sea, one question remained unanswered. If these currents are so perfect, so ancient, what set them in motion? What first stirred the ocean of space? No one had an answer. But somewhere far out beyond the reach of our telescopes, in the outermost arm of the Gaia, a faint light flickered, brief, rhythmic, familiar. A pulse. In the quiet after revelation, the universe held its breath. The currents had been mapped, the equations written, the poetry reluctantly accepted as physics. And still a single mystery remained: the light, a flicker too faint to catalogue, too rhythmic to ignore, emerging from the Gaia's farthest edge. It pulsed once every 16 hours. For a moment the world laughed. Coincidence surely. A star flare, an instrumental echo, a mirage of data. But the pulse did not vanish. It repeated, steady and indifferent to disbelief, as if mocking the limits of our skepticism. Telescopes turned their eyes toward the northern halo, their sensors stretched to catch the whisper of light, dancing at the threshold of perception. The coordinates matched nothing in any catalogue. No known star, no nebula, no remnant. Just darkness and rhythm. When the data was refined, the pattern emerged clearer. The pulse wasn't a single wavelength but a harmony. Light, radio, X-ray, each phase shifted in golden ratio intervals. The same proportion found in Atlas's dying echo, in Viriditas's heartbeat, in the geometry of the currents themselves. The same music, playing now from the heart of the invisible storm. For the first time in centuries, the language of science fell silent. No one wanted to speak the word forming at the edges of thought. Connection. Weeks passed. The signal persisted. The amplitude never changed. It neither grew nor decayed. It simply was. Like the tick of a clock that predated time. Theorists tried to model it, but equations failed. If it was mechanical, it should lose energy. If it was natural, it should drift in frequency. If it was alive, it should vary. But it did none of these things. It was static motion, a paradox rendered in light. When the first interferometric image was finally produced, a ghostly reconstruction built from thousands of hours of data, it showed nothing solid. Just a ripple, suspended in blackness, like the ring of a bell struck long ago and still humming. It wasn't a structure. It was an event continuing to happen. The scientists named it the still point. The name spread like mythology. It appeared in journals, in headlines, in whispered prayers. To some, it was the center of the galaxy's circulation, the anchor of motion. To others, it was a wound in space, the place where energy folded back into silence. To a few, it was something more, the moment the universe never stopped repeating. As the models matured, the idea took shape. The hidden currents weren't random filaments, nor relics of dark matter tides. They were echoes, the lingering vibrations of the universe's own formation. When the Milky Way was born, matter didn't simply fall together. It oscillated, rippled, and stabilized. Those ripples never truly stopped. They became the veins of motion, the rhythm of orbits, the pulse of Atlas and Viriditas. The still point wasn't new. It was ancient, perhaps the oldest thing we had ever seen. And if the currents were circulation, the still point was the heart. It didn't beat. It remembered beating, a remnant vibration from the moment the galaxy took its first breath. Once the idea settled, awe turned to purpose. Humanity, restless as ever, decided it had to go there. It took decades to plan. Propulsion wasn't enough. Traditional rockets couldn't reach the Gaia within lifetimes. But by then, the study of gravitational flow had advanced into navigation. Spacecraft could now sail the currents, adjusting their orientation to ride invisible gradients like wind. No fuel, no engine, just surrender. A slow dance through geometry. The first mission to the Gaia was called Astrea. It launched on the quietest day of the century, a thin silver vessel gliding outward from Earth with barely a sound. For 20 years it drifted, tracing the same path as 3IATLAS and 4I Viriditas, its sensors tuned to the rhythm of the pulse. Along the way it recorded faint tremors in the current, vibrations of gravity so gentle they felt like music. As it approached the halo, time itself seemed to soften. Telemetry began to stretch. Signals returned fractionally slower than they should. Not by distance, by something subtler, as though time near the Gaia's edge moved differently, curved inward like light caught in glass. And then, after years of silence, Astrea sent one final transmission, a short burst of compressed data, followed by 3 pulses spaced in golden ratio intervals. Then nothing. The data took weeks to decode. When it was finally reconstructed, it revealed no picture, no message, only a waveform, a pure continuous oscillation identical to the pulse from the Gaia. Astrea had become part of it. For the scientists, it was confirmation beyond question. The still point was not an object but a state, a resonance where motion becomes memory. To enter it was not to arrive but to join. One physicist, staring at the waveform late one night, wrote in her notes, "Maybe nothing truly leaves the galaxy. Maybe motion is simply how the universe remembers itself." That idea spread like quiet fire. The notion that every orbit, every wave, every particle was not moving through space but within the memory of motion itself. The hidden currents then were not currents at all. They were recollections. The galaxy remembering how it formed, replaying its creation endlessly, and everything within it, that stars, dust, life, were the echoes that keep it alive. In that sense, 3IATLAS had never arrived. It had returned. So had Viriditas. So had Astria. All travelers eventually flow back to the still point, the heart of motion, where even time forgets to pass. Years later, philosophers began to rephrase physics in the language of memory. They said entropy wasn't decay, it was recollection diffusing. That gravity wasn't attraction, it was the pull of familiarity. That maybe we too were part of the same rhythm, thinking structures formed in the galaxy's image, neurons firing like stars exchanging motion. Because when they mapped the frequency of the Gaia's pulse and compared it to the average firing rate of neurons in the human brain, the ratio matched. Not identical, but proportional. Another echo. The discovery didn't prove anything. It didn't need to. It simply deepened the mirror between cosmos and consciousness, both systems pulsing, both remembering, both living inside a current that had no beginning and no end. In the years that followed, space travel changed. The old engines grew quiet. The new ones listened instead. Humanity learned to drift, to move by resonance rather than resistance. And in drifting we found peace. The universe, it turned out, wasn't a battlefield of forces. It was a conversation between motion and stillness, between past and present, between matter and the memory that holds it, and somewhere far beyond the reach of telescopes, within the calm at the center of the Gaia, two tiny fragments, 3IATLAS and 4I Viriditas, circled forever in perfect equilibrium, their faint 16-hour pulse now part of the greater rhythm of the galaxy's heart. They were not messages, not miracles, not mysteries. They were proof that even the smallest travelers carry the memory of creation itself, because perhaps the ultimate secret of motion is not movement at all. Perhaps it's return. And as humanity finally understood that, the universe and vast, silent, infinite seemed for the first time to breathe in harmony with us. Not above us, not beyond us. With us the currents flowed. The heart remembered, and the still point, as eternal, patient, alive, went on pulsing quietly forever.